Good morning, everyone. I think it's about time to start. So welcome everyone to the second day of the Biocreative Evaluation Workshop. I hope everyone can hear me. Please confirm. Yes, perfect. So before we start, I would like to acknowledge all the participants and all the teams and everyone attending the workshop. Just a couple of general guidelines related to the evaluation workshop of Biocreative. So please make sure that you are muted if you're not speaking. So unless it's time you speak, then you can unmute. We have a question and answer box. So please type in your questions and we can collect them during the talks and try to answer all of these during the session. Otherwise, if we're running out of time, we might answer them in the chat directly. And also, please try to be respectful with the other attendees. So we don't want to have any harassment or intimidation of any person. Obviously, we have proceedings of the workshop, and there are technical details in terms of the participating systems. So they are all in these proceedings. The link is here and available online. We also have overview papers on each of these tracks describing how the data was generated, the result tables, and some details on the evaluation metrics and results. So if you're interested, please check out the proceedings as well. And we have today also a longer poster session with videos which are on YouTube. So thanks a lot to all our poster session participants. Some posters are directly related to the shared tasks, but we also have additional posters which are related to biomedical NLP of importance of the biocreative challenges. So yesterday, just to sum up, we had a very nice overview of the NLM Chem track done by the NCBI people, and also shorter talks on teams participating in this track. Then we had a nice keynote by Joshua Denny, and I think it shows us the potential on NLP and text mining also for electronic health records and extraction of phenotypes. And then we had the shared task on medication extraction in tweets. So today, following more like the named entity kind of task or entity linking of chemicals and drugs from yesterday, today we will follow up with a relation extraction task on chemicals and drugs and their interactions with genes, proteins, and microRNAs. And then we will have a session on posters, flash talks, short talks, very interesting ones, which we will play. And this session will be chaired by Risarta. And then we will have a panel session on more like the applied version of text mining, in this case, like challenges in mining adverse drug reactions. So Lynette will, and myself will chair this session, the panel. And tomorrow, we will have the other two tracks. So the Lit COVID track, organized also by the NCBI on a multi-label topic classification of COVID literature. And then we have a nice demo track on interactive text mining system for COVID. So I think that's basically it for today. So let's get started. And remember, please post your questions in the chat. So I will stop sharing the screen and hand over to Antonio to actually try to set up the first session.
Okay. Yes. Thank you, Martin. Thank you for the introduction. As Martin said, we are having right now the drug prod session of the Biocreative 7 workshop. Drug prod is the track 1, the text mining drug and chemical protein interaction tracks of Biocreative 7, and we will start with a 20 minutes, more or less 15-20 minutes overview, and then proceed with the participant videos. Drug prod was due thanks to the collaboration of the Barcelona Supercomputing Center, my institution, and the University of Turku, and people from there, Farouk, Juni, and Sampo, who are here attending the workshop as well. So thanks to this collaboration, we were able to go on and to make this happen. Chemical and protein chemical and protein interaction or chemical and gene interactions are relevant in the different fields. We know they are relevant in the molecular biology or system biology, but they are also important for medicine, for drug discovery, for precision medicine, etc. And we have we distinguish here in DrugProt three types of chemical protein interactions. On the first, we have those related to metabolic relations, and they are involved in the metabolic pathways in drug-drug interaction, etc. But we also, since chemical protein interaction are at the core of every living beings, we know that, for instance, they are very relevant in drug design and drug discovery, and finally also very present in the models of drug response due to their role in the regulation and gene expression and modulation of gene expression. And for example, we have relations and interaction of up or down regulation or modulation of gene expression. Due to this ubiquitous of the relevance of chemical and gene interactions, we have many resources, many databases that collect information about chemical and gene interaction. And we have here a plethora of them, but there are many more. And some of them are very focused on a specific type of interaction, and others are more general. But what they have in common is that they usually rely on manual curation of literature, and this is a high intensive process. And for example, during the situations like the COVID pandemic, in which there was a really high production of biomedical literature, it was difficult to be up to date with this constant publication of new literature. So this is where the text mining and NLP can play a role and make more efficient this extraction and this structuring of chemical and gene interaction from literature. This interaction, we have to take in mind that we have three factors. We have the compounds, and we had previously biocreative tracks on extracting those compounds, and we had a really nice example yesterday of the first session we had from full text articles. And the second aspect are the genes, and we have also had biocreative efforts to extract genes, and finally the relationships. And there has been previously efforts on extracting such relationship, and for example, we have in biocreative 6 the ChemProt on chemical and gene interactions. However, ChemProt has some limitation related to the granularity, the exploitation, and that is why we have done this year DrugProt to let's say correct and these limitations and improve the impact. In ChemProt, we had the participant had to extract groups of relationships, but in this year in DrugProt, the goal is to extract relation types, which are based and annotated based on annotation guidelines of the relationship, and these guidelines were done after an intense review of previous resources. I want to highlight here that the existence of annotation guidelines, it is very relevant, because only with annotation guidelines we can understand the output of the systems, and only with annotation guidelines which are public, and you can go to this link to get them, you can modify, extend, adapt this corpus to other use cases. The generation of the DrugProt data had two phases. In phase 1, we extracted, we annotated we did the name entity annotation that was done previously. We and in phase 2 we annotated the relations. And indeed, the goal of the participants, it is to extract novel relations in the test set given the entities. The entities are already given to the participants. So the goal of the DrugProt is to focus on the phase 2 in the relation extraction. So I talk about the corpus, and this is the overview. drag prop corpus, it is a huge corpus. The complete gold standard has 5,000 documents with more than 120,000 manual entity annotations and more than 24,000 manual relation annotations. And this allows the use of highly intensive deep learning model, for example, as we will see in the participant talks. But also another novelty of the drag prop track is that we include a subtrack on large scale knowledge graph generation, in which we give to the participant 2.4 million documents and with entity annotations, with 55 million entity annotations, and they had to extract the relations. And we finally got 146 million predicted relation from the participants. So the numbers, the volumes we are talking here are huge. And if we go into the detail of the distribution of the different relation types, because we said previously that we annotated, we had 13 different relation types, and these are granular and exhaustive. And this is partially why the outputs of the system are ready to be used in a final use case. We see that there are relations that are more ubiquitous than others. For example, here the inhibitor relation type is very present in the both training, development, and test set, but there are other relations such as agonist, activator, or inhibitor that are more scarce. This is actually one of the values of the track, because this is the realistic setting. This is what happens in PubMed. We have not artificially modify the corpus so that because in this way we represent what is actually present in PubMed. And that was the statistics of the gold standard set, and this is how the large scale corpus was generated. The subtract on large scale knowledge graph mining included a 2.5 million abstract corpus that were selected following document selection criteria that were carefully defined, manually defined, to enrich the drag prop relations. And we had criteria based on mesh search or based on a document classification, etc. You have here the link to the Zenodo, where this document collection protocol will be is already public, so that it is everything is transparent and can be replicated. Once the documents were selected, were downloaded from PubMed, they were automatically annotated with almost 54 million entity annotations. And this was given to drag prop participants. And we already examined the motivation and the resources, but what was the community response? Well, we are glad to say that the community reacted marvelously. It was great. We had more than 100 registrations, and finally 30 participating teams, and in the main track, and 9 participating teams in the large scale track. And this was so far the largest participation in a biocreative track, which is awesome. And also we had people coming from industry or also from academia, people coming from Asia, from Africa, Europe, US, America. So it has been a great response for the community, and we are really glad to that happened. And this is probably the slide many participants were waiting for, and of course many other attendees. This is the official. This has the official results of the best run across all 13 drag prop relations. Since we had so many participants, we had to split the table in two, but it is the same table, and ordered by F1 score. F1 score was the main metric, and the other metrics present here are also the micro average precision and micro average recall. And we see that if we have a look at the drag prop main track, which are the first columns, there are many teams with F1 scores close to 0.8, which is close to human performance, and that is awesome. The methodologies used by those teams were astonishing, and they did a fantastic work, and the results prove that. But also, if we look at the other metrics, at the precision, for example, which can be very relevant to build a knowledge graph, we had different teams obtaining precisions close to 0.8 in a setting which is very complex and extracting relations that are very complex. So this is very impressive work. And last conclusion from this table, let's move to the large scale knowledge graph track. We wanted to assess not only if the participants and the methodologies obtain good metrics, but also we wanted to assess whether those metrics maintained if we want to scale to a large document collection. And indeed, this is what happens. We have in the large scale track different teams obtaining also F1 scores close to 0.8, precision close to 0.8. So those teams manage not only to make a really good system, but also to make systems that scale properly to large volumes. And if we have a look at the results per relation type, and this is very relevant for the final application of these systems, we see that despite, of course, there are differences because there are relationships more complex than others, relationships with more support than others, or with more annotation consistency than others. Many of them are predicted very well by different participants. And even for the antagonists, we had the NCBI team with reaching almost 0.93 F1 score, which is awesome performance. And finally, from here, it is also remarkable that there is not one team dominating all the relation types. We have, for example, the NCBI team obtaining the best, the highest F1 score in antagonist or agonist or substrate relation types. Also, we have Bibliome team obtaining really good performances in activator, or the Humboldt team in the indirect regulator, etc. So there are different approaches or different architecture modification that work better for one relation type, and others that work better for others relation types. Looking at the large scale knowledge graph results, let's recap. We had here 9 teams, 21 submissions in total, 13 relation types covered by those submissions. And if we can create a knowledge graph per submission for each of the 13 drag prod relation types, obtaining 273 knowledge graphs. For example, we have here the overview of an example of a knowledge graph created with the predictions of the NCBI team for the antagonist relation. And in addition to having awesome metrics, the number of relationships, it is also very high, almost 200,000 relationships. And how did the system, the participant obtain such a good result? Well, we will have a detailed look at this at the later talks, but most participants use a transformer language model for encoding the sentence information, pre-trained transformer language model, and then applied a classification head to the last layer and did the sequence classification. We also did a survey to asking the participant which kind of language model they use, and these are the results. BioBERT and PubMed are the most used. And a second of the important point here is that most participants did some kind of ensembling. They trained different models and then did, for example, majority voting or other more complex approaches. And just two flavors of some common architecture variations are in the pre-processing step, deciding whether doing entity marking or entity masking, and also modifying the classification head. As said, in the posterior talks, we will have a detailed look at this because the authors will present their work. I just want to highlight here three of the top performing teams, which are Humboldt, NCBI, and KUAZ. They used a language model, a transformer language model. They did some kind of assembling. But for example, Humboldt team, they enrich the encoding part of the system with entity description. Also, NCBI, they included they ensembled not only sequence classification system but also name entity recognition system to get more information. And finally, KUA set team did fantastic work in that documentation. So we are reaching the end of the overview. As conclusions, we are very lucky. We are very glad that we got a fantastic response from the community. It was the biocreative track with the larger number of participants, I believe. And well, this is in part because the drug product resources were also very interesting. We have 3 annotation guidelines, 2 entities, 13 relation types, and the final corpus is among the largest ones in the for entities and relations in the biomedical NLP domain, with 100,000 entities and 24,000 relations. From the methodological point of view, most participants did some kind of ensembling of pre-trained transformer models combined with ontology information. And these systems achieved close to human annotation quality for many drug product relation types. Finally, thanks to the large-scale knowledge graph track, we saw that those systems are scalable. Some of them are open source, and we can build a large knowledge graph from their outputs, and also we can release a large-scale silver standard with their predictions. And as future directions, we propose the manual validation of this drug product knowledge graph using a community curation effort. We also see the need of applying these large-scale systems to, for example, other data types such as full text or patents, and also to explore the knowledge graph as soon as it is published for drug discovery, drug repurposing, orphan gene mining, etc. Finally, 2 more points, which are we plan to include also other relations that were not included in drug pro, such as modulator or cofactor, and the silver standard generated that in the large scale track that is good for generating a knowledge graph can be used to retrain relation extraction system with automatically annotated data, high quality annotated data. So I leave you here some links. We will put the links also in the chat, so that you can go and check the corpus, evaluation library, etc. And also a Google form here to the Coda Lab, because we will put the test set in a Coda Lab together with the evaluation library so that everybody can test their new systems. And finally, just thank you to all the people here, also all the teams, participating teams, my institution, the people at the Turku University, organizers of BioCreative, and also Chemprod collaborators. Thank you, and I'm open to hear your questions.
So, Antonio, thanks a lot. So I think it's time to answer questions. I think there was quite a lot of information in the overview talk. So please do either, type the questions in the chat. Antonio, maybe you can see it. So you've seen the questions in the chat? Yes?
Yes. I'm seeing the last question. Can you talk a bit more about how you annotated the large scale data set? This was done thanks to the collaborators of the University of Turku. They train a system, a name entity recognition system on the drug product entity annotations, one for the chemical and one for the drug annotations, which obtained higher than 0.9 F1 score. It was a great work, and these taggers were used to generate the annotations of the large scale set. So these are almost all of them are automatic annotations with a small set of manual annotations coming from the gold standard.
So to complement this answer from Antonio, so the official drug-pod NER systems, there's the NER chemical and the NER gene system. So these two drag-prot-NER systems, they will be released. So I think here our collaborators from Turco, Uni and also Sampo and Farouk, they are here. They can comment on that. But these will be the official named entity systems we actually, sharing. We'll share with the community as an additional result of this drag beyond the relation extraction.
Okay, maybe I will reply one more answer and then go to the next talks, Martin. Okay, about the test dataset, will you make it publicly available? No, it will be hosted at the Coda Lab, and in the Coda Lab, we will have the test set and the evaluation library, and so that it will remain hidden to maintain the fairness of the competition. But everybody will be able to test their results with this test set, so that we can compare everybody's result across time and hopefully for many years. So it will be put in Coda Lab and will remain there.
So thanks a lot, Antonio. I think there will be a couple of more questions. So if you have questions and you didn't dare to ask, please type them in the chat. We will try also to answer them during the session of today. So I already see here a question related to the use of Campbell papers and I've seen some other questions. So please, everything you would like to know about the track or even suggestion for the future tracks and knowledge graph exploitation, send them in the chat and contact us also if you have more questions. Antonio, maybe you can proceed with the systems talk.
Yes, so now we will have the participant talks, describing their systems, and the first one is Wang Jin, a PhD candidate from Korea University. So please go ahead. Stacy is yours.
Hi, everyone. My name is Won Jin Yoon from Korea University, and today I would like to introduce our team's participation at the BioCreative Challenge. We are a joint team from Korea University in South Korea and AstraZeneca from UK. So here's our motivation for our participating system, that building a biomedical NLP datasets are scarce resources because the experts should label the data, and that cost a lot. So it is expensive to build the biomedical NLP datasets. So it is difficult to build a high quality and also large scale bio-NLP dataset. And so in order to alleviate this problem, researchers, including me, myself, utilize unlabeled dataset, and because that enables models to learn from the large scale data. So existing methods and existing researchers usually utilize those two approaches. The first one would be a self-supervised learning, and the second one would be a data augmentation method. And so here's the simple example and explanation about that unlabeled data, utilizing unlabeled data. That the first one, self-supervised learning, pre-trained language models like bots or Robota or GPT or other language models, transformer-based or other architecture would be a self-supervised learning. And another branch, data augmentation method, there can be several method. The first one would be a distantly supervised dataset created using knowledge bases, and the second one would be a model generated labels to augment the existing dataset. In other words, researchers have called it as a weakly supervised learning or weakly labeled dataset. But the problem of those data augmentation method is that they add noise to the augmented dataset, and maybe the upper bound of augmented data might be restricted to the original data or some other restrictions. So, but what I have focused on was that those noises comes from a different nature. I mean, noises from those two methods originated from different reasons. So let's look at the diagram down here. That small area means small area means diagram here. Small area means that small noises, which means good quality augmented data set. So when we take a look at the noise from distant supervision, that there can be several reasons for those noises, but what comes first to my mind is that knowledge base might contain incomplete information. And another reason is that because we use simple exact matching schema to annotate, that means we can say that as a crude matching system. So even for semantically irrelevant sentences can be marked as a positive sample. So here you see the noise from distant supervision can be this big at the entire circle. And also when we think about noise from model generated with labels, the labeling noise that the original data set inherited to the generated data set. So this sets like upper bound for the augmented data set. And also I think this is one of the biggest thing we need to think about, that model performs fully for some novel data points that if the trained data comes from this different distribution of training data set, then the model might produce long label. At least the model may be weak for those labels, and the augmented data set generated from those model might not perform well for those novel data points. So that this method also has quite a large noise. So my idea is that by exclusively using those to annotate those two methods, then we could reduce noise to intersection of these two sets ideally. But reducing noise in weak labels by filtering long samples with knowledge base. So we use knowledge base to check the validity of predicted labels. So we drop generated data samples that do not agree with knowledge base. So that was our motivation. And here's the simple figure to show how we did it. So we used direct data set to train language model, and using that language model, train the language model to predict labels and filter out the predicted labels with knowledge base to make a augmented data set. We use a Ctd data set as a knowledge base. And here's some settings for our method that we use a sequence classification model, which utilize CLS token for classification head and using linear layer. And also we did not anonymize, and we used 4 markers, and we also split entire paragraph into sentence level input using standard library. And we used BioRM language model, which is based on Robota large pre-trained on biomedical corpus. And we also used ensemble method 10 or 5 on learn with different random seed. And we also use training dataset and development dataset for training. We merged them and divided into 10 partitions, and we use 9 partitions for training and 1 partition for development set, and example those 10 models as we do on cross validation. So here's the results for the development data set, and we observed that 1 point gain across all the settings like language models or other entity anonymized method, and it seems like the method works quite well. But when we get the results from test data, we observe that there's a little bit inconsistent result at the test time. We might think that difference comes from that we use different settings for ensemble method, that we did not have enough time to train 10 models for this augmented data method. So we simply used 5 on, but we used 10 models for non-augmented data. But
please, you should be finishing.
Yes, but we observed a constant gain in recall, and as you can see in this red box, and using that train plus step for training was effective, which we can see on the blue box. So we have another interesting findings, but because we do not have enough time, so please contact me on email, or please refer to our proceeding our technical report. Thank you.
Thank you, Wanjin. It was great. Sorry, I had to interrupt you at the very end. I asked the following speakers to make the presentation in the predefined time, so that everybody can have enough time to describe their systems. And I wanted to give you some very quick questions. You use this filtering method to refine the data augmentation dataset. Did you also use some post filtering for the final results, or the final results are just straight what the model outputs?
We did not use post processing for the final output. So we did use some post processing step for maybe this making augmented data set, but for the final output of our model did not utilize some serious post processing method or some other methods. It was simply a merge of output of the model. Thank you.
Okay, thank you for the great work and the great talk. The next speaker, it's Ling Liu, that is a postdoc fellow at the from the NCBI team. So please go ahead. The stage is yours.
Hello. Can you see my slides?
Yes.
Yes. Great. Thank you. Hello, everyone. My name is Ling Liu. I'm postdoc in BioNLP group at NCBI. Thanks for inviting us to present our work in the DRAG Pro track. The DRAG Pro track aims to extract drug protein interaction from PubMed abstract given the gold standard entities. There are a total of 13 relation types. According to the feature of the corpus, only less than 1% of the relation are crossing multiple sentences in the training set. Therefore, we focus on the training of the relation extraction within sentence. We developed two independent deep learning-based approach based on the biomedical pre-trained language model, as shown in the figure. One is the traditional text classification framework. Besides, we also explore a novel sequence neighboring framework. Then, voting ensemble methods are further used to improve the final performance. In the text classification framework, we treat the text as a multi-class classification problem. We represent a sentence with a drug protein pair using two different ways. The first representation is to insert entity tags in front of the drug and the protein mentions. We also treat the entity name tags as the first sentence and use the SEP tag to concatenate it with the first way sequence as the second representation. Since keeping the orange entities in the sentence bring higher performance, our method doesn't replace the drug and the protein entity to the text. Then we use a biomedical pre-trained model to classify the text into a relation type. We also proposed a novel sequence neighboring framework to address the text. Different from the text classification framework, the text is converted to a sequence neighboring problem. Given a candidate source entity in sentence, example drug entity of occurring in the figure, the goal of the model is to recognize all the corresponding target entity involved in the relations. Here are protein entities of PDE5 and PDE4. We design a simple and effective tagging scheme for this text. For the input sequence, we insert argue1 pair in the beginning and end of the candidate source entities. Besides, drug pro tag pairs are inserted in the beginning and end of the drug protein mentioned to acquire the entity tabs and the boundary. For the output sequence, the token involved in the relations will be tagged by the relation tab, and we use the label O to represent other tokens which do not enroll in a relation. We evaluate the 5 biomedical pre-trained model through the sequence neighboring method. To further improve the performance, we tried 3 ensemble methods. For the majority voting, we select the relation that are repredict by more than half of our model. In addition, we search by word and random to find a subset of our model that may achieve higher performance on the development set than using our model. During the task, we submitted 5 rounds as our final submission. For round 1, we merged the official training and development set, then random select 350 upstream as our development set for early stopping. Only sequence neighboring model are assembled with the majority voting. Round 2, we use the same model and the ensemble method. Different is we use only the official training set for model training and early stopping according to the performance on the official development set. Round 3, both the text classification and the sequence neighboring model are assembled by voting with backward search. Round 4, the model are assembled by the voting with random search. Round 5, all model above mentioned are assembled by the majority voting. Finally, an ensemble of 2 framework model with majority voting achieved the highest over F1 score on the main test site. We also participated in the additional large scale test. We did not use all model to predict the result due to the limitation of the TAN and the GPU resource. Instead, we select 4 eventual model according to the performance on the development set, then use different combination of them with the majority voting to generate our submission. Each model took about 5 days for predicting the large scale test site on 1 GPU. Similar results are observed on the large scale test site. In summary, we propose a novel sequence neighboring framework. Its performance is as good as traditional text classification, even achieve better performance. We tested many biomedical pre-trained language models, and there was no clean winner. In our methods, we did not use any additional resource and post-processing. How to use additional feature to improve the performance is one of our future directions. After the release of the gold standard task set, we will do error analysis and we will do more comparison between the 2 frameworks. Finally, thank the organizer of the task and thank our team member, my colleague Protein, Zhixuan, and our PI, Dr. Lu. This research was supported by the NLM. Thank you for your attention.
Thank you, Ling. It was a great presentation, and also the work you did was awesome. I would like to ask you, because it is interesting that there was no difference in using almost in performance between using the backward search or majority voting. Do you have any idea why these ensembling techniques did not have that much impact in the final performance?
Your question is about the ensemble methods.
Yeah, there are 3. You're using different ensemble methods,
yeah.
But at the end, there's no much difference between the performance of the majority voting and the performance of the backward search, right?
Yes. We use 3 ensemble methods, but they have not achieved a significant difference. The voting with random search and backward search use development set. I think the performance is overfit the development set. So in our experiments, the three methods have no significant difference. Thank you.
Okay, so next, thank you. Next speaker is Xin Xiu from the Florida State University. Please go ahead.
Okay, can you hear me?
Yes.
Okay, sure. Hello everyone. My name is Shane from the Department of Statistics in Florida State University. Today I'll be talking about text mining drug-protein interactions using an ensemble of BERT, sentence BERT, and T5 models. This project is done by me, Wanjing Wang, and Jinfen Zhang. In the dataset, we found cases with multiple annotations. For example, in the sentence below, the relation between NFD and MMP9 is annotated as both indirect downregulator and inhibitor. There are 430 such cases out of 17,288 cases in the training set. Because the ratio is very small, we ignored this and still use single label classifiers. We also found overlapping Ndt annotations. For example, in this sentence, two entities are annotated, GABA type 1 receptors and the GABA. Based on the annotation rule, we let all of them have a false label. When processing the data set, we mask entity names with two special tokens, ChemName and GName. For submissions 1 and 2, we used the BERT model. We took the pooled output of the CRS token, passed it through a dropout layer, then a linear layer, and a sigmoid function for class probabilities. For pre-trained weights, we found PubMed BERT trained on full text articles yielded best results. We also trained we also used the data augmentation technique. We first trained the BERT model, then found out all mispredicted sentences. For each of them, we removed a word not in the shortest path between ChemName and GName to construct new sentences. We believe these newly constructed sentences are similar to the original ones and can help the model on these mispredicted cases. For all models to follow, we also use this augmented training data set to fine-tune. And here are the BERT results. For split 1, we use all training data set as our training set and all development data as a validation set. For split 2, we combine training and validation data set and use a 4-1 split on articles to get our training and validation sets. For all following models, we use split 2. For submission 3, we use a T5 model, short for text-to-text transformer. It is an encoder-decoder model based on transformers that for every text input outputs text as well. In our application, we treat the labels as text when fine-tuning the model and use the Sci5 as our initial weights. Sci5 is trained on large biomedical corpora. See below for the performance of our fine-tuned T5 model. We also use the sentence BERT model to train embeddings of sentences. We use the batch-hard triplet loss when training the sentence BERT model. To calculate the layer loss for any selected sentence, we call it the anchor sentence. We first find a positive sentence that has the same level and a negative one that has a different one. Given any distance we measure d and a margin m, the triplet loss is defined as follows. We want the distance between the anchor and the positive to be smaller than that between the anchor and the negative by at least m. For the batch hard triplet loss, we found the hardest positive and negative sentences within the mini batch. Although not submitted because we are only allowed to submit 5 results, the sentence BERT model has 3 uses. First, use the k-nearest neighbor to train a classifier. Second, do clustering and help with model ensemble. And 3, sentence embeddings make more tools accessible for analysis. We use 2 types of ensemble methods. The majority vote algorithm takes the most voted label among BERT, T5, and sentence BERT models. Whenever there isn't a majority, we take the prediction from the base model that gives the highest F1 score on the validation set. The trained ensemble method is based on the idea that individual model performance may differ in different clusters. We first cluster all sentences based on its sentence BERT embeddings and train a classifier using the following features and response. For features, we use the cluster ID, class ID from sentence BERT, class layer BERT vector, and class probabilities from BERT. For the response, we use whether the models predict the labels right. T5 is not included because our time was limited. Here are the results for our ensemble models. The majority vote algorithm yielded the best result in both validation set and the test set. We believe that there are some issues with the test results for the trained ensemble. Here we show the granular results by relation type obtained by majority vote algorithm on the development set. We show 2 observations from our analysis. First, agonist activator, agonist inhibitor, and substrate product combined only have 67 out of 17,288 instances. I think this is the reason that they have a 0 F1 score. Second, we analyze the part of label when they have the relative poor results. Thanks to the sentence word embeddings, we can find instances that none of its 10 closest neighbors that our model predicted right. Using this technique, we are able to find several cases that we believe are mislabeled. An example is shown here. And finally, thanks everyone for coming to this talk, and thanks for the organizers for giving me this opportunity. Hello?
Antonio, Martin, you there?
Okay. Yep. Yeah. Sorry, had a small connection issue at the very last moment. But thank you for the presentation. It was a great one. I would like to, because you mentioned you combined or tested like BERT model with also T5, which is more text to text, right?
Yes.
And do you have any preference in terms of using one of or the others? Because yesterday we had the people from NVIDIA saying that it is very promising what text to text models can do. Do you have any preference or thought about it?
Well, yeah, this is definitely, T5 model is definitely one of the more recent advances in text mining in general. And so I think there are some room to explore in using that model in biomedical text like this research. And I personally don't have much preference. So whatever result is better, we just use that one.
Okay, great. Thank you for the fantastic talk.
Thank you.
Okay, we have one last question from Martin. Did you explore data augmentation techniques specific for each of the relation types, or are they general?
No, we didn't explore it. We just studied in general. They each explore in general, not for every relation type.
Okay, thank you for the question, Martin. Next speaker is Leon Weber from the Humboldt University Berlin. So please go ahead.
Hi, can you see my slides all right and hear me?
Yes.
Yes.
Awesome, thanks. So hello everyone, my name is Leon Weber. I'm a fourth year PhD candidate at Humboldt University in Berlin. And this is joint work with Mario Sänger, Samuel Legada, Fabio Barth, Christoph Alt, and Ulf Leser, also from Humboldt. So let me describe our contribution to the drug broad shared task. When we started out working on the shared task, we wanted to decide on a general classification framework, and we decided on relation classification because in our experience, it's a very robust framework for relation extraction. So what that means is that given a sentence with annotated entities, we construct one example for each valid entity pair. So in this case, for each chemical protein pair, we construct one example, we mark it up with special marker tokens, and then we feed it through a standard sentence classification model that can do multi-label classification, right? And now, obviously, we wanted to improve on this framework for this shared task. So we thought about a lot of different modifications that we could try. Then we tested different combinations of those modifications with the Hydra configuration and sweeping framework. And to give you some idea, there's totaled in over 2,000 runs in which we tested different modifications and hyperparameter settings. So to give you a brief idea of what worked, what he tried, and what worked and what didn't, here's a list. So what red means is that it works worse than our unmodified baseline. Green means it worked better, and black means it didn't make much of a difference. So we tried adding additional or auxiliary data based on different schemes. Unfortunately, that harmed the results. Also, introducing a threshold per class with different schemes didn't help. we tried using relational knowledge base information in the form of text or knowledge base embeddings. This also harmed performance. Then what didn't matter much was what final representation, whether the class token or the entity markers or both we used for the sentence classification. Also, whether we use entity masking or not didn't really make much difference. What we found a lot of variance in using different pre-trained transformers. Yeah, we tried a lot of them. Also tuning the random seeds, a bit hacky, but it still worked. And optimizing hyperparameters for learning rate, maximum number of epochs and maximum length of the sentences was important. Our main finding is this, that adding textual entity descriptions had an impact and improved results quite a bit. And also, this doesn't come as a surprise to many of you, I think, ensembling helped a lot, right? So this was were preliminary runs, and now we took everything that worked and we built our final model on that. So we used the Roberta large model by Facebook that was trained on PubMed and Mimic. We tuned the random seeds, we set the optimal hyperparameters, and we harvested entity descriptions for the chemicals from the Ctd database by normalizing the chemical mentions with biosyn, and then appending the textual chemical descriptions to our input examples. And yeah, we did tenfold ensembling by training 10 different models across 10 different random seeds and then averaging the logits. So until now, everything we tried was on the development set, and in the past we made the observation that in such tasks one might overfit on the development set. So we actually wanted to check whether our modifications are robust on the test set. So this is how we designed our runs. Here we plot the relative improvement of our model over our baseline run, in which we don't use chemical descriptions and don't use ensembling, but we train on the union of train and development. And if we then add entity descriptions to that, that helps a bit. Tenfold ensembling helps a lot more. If we do both, but leave out the development set, this is even better. And if we then add entity descriptions, tenfold ensembling, and train on the train and development set, this leads to our highest score, which is 79.73% F1. So then we were interested in a quick error analysis. So we looked at how well our model performs across different relation types. This is a plot of the F1 score per relation type and by the number of training examples. And we can see that the results vary a bit. So there are classes for which the results are quite good, classes for which results are quite bad. And we found that there's a moderate correlation between the number of training examples and the performance. To conclude, we've modeled the drug-bot relation extraction as a relation classification task. We've evaluated many different modifications using Hydra. I can warmly recommend this framework. It is really fun to work with. The main findings are that textual chemical descriptions, ensembling, and training on train and development led to improvements. And in the future work, we want to integrate this model into our standalone biomedical relation extraction tool Pebble, so that domain scientists can actually use it. And we want to investigate generative approaches for zero and few-shot learning to help with underrepresented relation classes. Thank you very much for your attention. I'm looking forward to the questions now.
Thank you, Leon, because you got fantastic results and did a great work. We have a couple of questions for you. First one, why did you decide to use Ctd description? And did this improvement affect all relation types?
So first question, why did we use Ctd? Actually, we also used, I think, drug bank descriptions and different fields from drug bank and Ctd, and we evaluated all of them, and Ctd just worked. Everything else didn't work. Also adding textual descriptions for the proteins didn't work. So that's why we used Ctd. The second one, we haven't checked. That's a very interesting suggestion. Thanks. So we will check whether entity descriptions help for all relation types or only some.
Okay, and I think you just replied the question from Ling, because he was asking why only use chemical and not gene descriptions, and you said that that didn't improve, right?
Yeah, and also we run into the length limits of the transformer if we add both. Then we have to truncate something, and that's never nice. So we tried, it didn't work.
Okay, great. Thank you for the replies. And let's go to the next speaker, that is Anfu Tang from the l'Institut National de la Recherche Agronomique. So please, go ahead.
Hi, everyone. Can you hear me?
I do hear you, but I do not see the slides right now. I saw them briefly for a couple of seconds.
Do you see the slide?
Yes,
now?
and I hear you. Yep.
Hi, everyone. I'm a PhD student from the Paris-Saclay University in France. And today I will present the methods that we used during the drug pro challenge for the team Bibliome, which is the name of the group in which I currently work. Our system is based on domain-specific BERT, more specifically BioBERT and SciBERT. The main difference between domain-specific BERT and validated BERT is that domain-specific BERT is pre-trained domain-specific corpus. For example, BioBERT uses PubMed abstracts, which is biomedical, and SciBERT uses collected samples from Semantic Scholar. We loaded pre-trained weights of these models by Hugging Face in our experiments. We made a hypothesis that integrating syntactic information into BERT may improve its performance. And here we propose to integrate constituent information. As shown here, we keep the noun or verbal phrases at the deepest level in the constituent tree to separate the sentence into chunks. We suppose that training a subnetwork on these chunks will help integrate constituent information into our network. The whole architecture of our neural network is simple. Between the pre-trained BERT model and the linear layer that we use in a standard fine-tuned network, we add two attention layers. At the output of the pre-trained BERT, we get contextualized word piece embeddings, and with some embeddings of word pieces that belong to the same constituent to get the constituent embeddings. These constituent embeddings will then be fed into the newly initialized attention layers, and we suppose that interactions between constituents can be captured in this way, and they will be useful for relation extraction. We have submitted 5 submissions by making ensembles of different combinations of models. And there are 3 types of models, BioBERT, SciBERT, and const-BioBERT. For each ensemble, we train 8 models with different random initializations of weights and use majority vote to get the final prediction. We keep the same hyperparameters for training and use early stopping to control the training process. The loss function for fine-tuning is weighted, and we find that using a weighted loss function improves the model performance on the validation set. For each class, the loss is weighted by the ratio of total number of training examples and the number of training examples labeled in this class. And here are the results of our different submissions. We can find that integrating syntactic information does degrade the performance, though not much. By comparing the result 1 and 4, we observe that unlike SciBERT, the const BioBERT seems to make consistent predictions with BioBERT. And if we compare 2 and 5, the comparison between the results 2 and 5 confirms this observation. Besides, we investigate the performance of our methods on these 3 classes with few training examples. We found that our 5 ensembles obtain a 0 or close to 0 F1 score on these classes, but for different reasons. For models without syntactic information, we score 0 on these classes because we did make some predictions on these classes, but they are not correct. But for these models with syntactic information, no or much less examples are predicted in these 3 classes. It means that integrating syntactic information makes our prediction more conservative. And the natural explanation for the degradation is that in our networks, there are 2 layers that are not pre-trained, and fine-tuning does not train this layer sufficiently given the size of training set. Another possibility is that BERT has already learned the chunking information, thus manually integrating this information into BERT does no good, but also no harm. Maybe the chunking information is too basic and learnable during the pre-training of BERT. And what we need to do is to incorporate more advanced, for example, hierarchical information about the constituent tree. And in the future, a possible solution to do that is to replace the 2 attention layers by a 3 LSTM layer. Thank you.
Okay, thank you. I would like to ask you, Anfu, what would you need to participate in the large-scale track? Could you need more hardware resources or the changing the system?
I think our system is already we can already use this system for large scale track. But we didn't do that because at the time I did not have enough calculate resources to do that. But it is already I think it is ready to use.
Okay, great. Also, Martin asks, did you examine the performance of const BioBERT depending on the training size, or if the number of entity co-occurrences in a sentence did have some effect?
I think that's an interesting proposition. I have not do that. I didn't do that, but I think it may be. I think it is interesting to investigate. Thank you.
Okay, if there are no more questions, thank you, Anfu Tang from the l'Institut National de la Recherche Agronomique. And the next speaker is Virginia Adams, applied scientist at NVIDIA. So please, Virginia, go ahead.
Can you guys hear me?
Yes, and we see the slides.
Okay, great. Hi, I'm Virginia Adams, and I'm an applied scientist on NVIDIA's conversational AI team. Today, I'm going to be presenting to you guys my team's submission to the Track 1 relation extraction tasks as part of the BioCreative 7 workshop. So first, I want to introduce my team. Sorry, there's a pop-up. Okay, first I want to introduce my team and myself. There's Hu Chang, Anas, Bo, and Carol, all of whom worked really hard on our submission. Okay, next, I want to just introduce the grand vision that we had at the onset of working on this challenge. So we're asked to do relation extraction on given a chemical and a gene. We're asked to predict the relationship between those 2 entities and that exists in a sentence giving context to both the gene and the chemical. Because we were participating in this track and several other tracks as part of this workshop, we decided to try a unified model that could do a bunch of different tasks at the same time. Specifically, we decided to try a prompting approach to relation extraction, in which we use a pre-trained generative language model, and we formulate relation extraction as a question that we ask specifically in our case, T5 or GPT, to perform relation extraction, and expected to predict an answer, which is the relationship between two specific entities in the sentence that we specify beforehand. Before I dive deeper into how we formulated relation extraction as a text-to-text or prompting task, I want to talk about our baseline system that we use to compare our text-to-text system with. Our baseline approach is a more traditional approach to relation extraction, in which we use just a BERT-based encoder and then two fully connected layers that predict a probability distribution over the 14 possible classes for the different relationship types, where one of the classes is no relation at all. On the screen, I have the two different pre-processing annotation types that we tried for this for our baseline model. On the right-hand side, we tried masking, where we mask every chemical and every gene in an input sentence, and then the specific chemical and gene that we're interested in get a mask to indicate that those are the two entities that we want to predict the relationship between. The idea behind masking is to keep the model from overfitting to specific relationships seen in the training set, because chemicals and genes obviously can have different relationships depending on the quantity of the chemical or the gene or the environment that they're in. On the left-hand side is the other annotation format that we tried, where instead we just completely ignore the other genes and chemicals in the sentence and then add tags around the specific gene and chemical that we want the model to predict the relationship between. Our best submission was a biomegatron encoder, where we use the annotation format on the left-hand side, the masking format, but we didn't try the other types of encoders with, or sorry, we didn't try biomegatron with the tag format because of time constraints, so we can't say one format was better than the other. And then here are our results on just our baseline approach. As you can see, we tried with BERT, just BERT base, BERT large, BioBERT, and biomegatron. We generally saw the trend that larger models are better, larger encoder models are better at this task with a fixed set of fully connected layers. And then also the case vocabulary also worked better compared to uncased. Okay, so let's talk about how we turned relation extraction into a text-to-text task. So we started off a bit ambitiously, where we gave, this specifically was for GPT, we gave the model an entire paragraph, and then we created this grammar where we pulled out the specific entities occurring in that paragraph that I have highlighted in yellow. And then we had chemicals that I highlighted. We labeled each entity as a chemical or a gene that I have highlighted in blue and pink with identification numbers. And then we expected the model to output what we have at the bottom underneath the ground truth, the word ground truth. And then where it just pulls out the chemical ID and the gene ID for the entities that it's referring to, and then the specific relationship that I have highlighted in green. Because these models have max sequence length as input, we ran into sequence length issues and decided to move on to a different type of approach, a more human text-to-text approach, in which we say find relations and we provide it the context sentence, and then expect the model to predict, to output both the chemicals that it's identifying a relationship between and also what the relationship is. The issue with this approach is that the model would only usually outputted just one relationship instead of the litany of relationships that could be present in the sentence. And also the model rarely outputted none, even though most of the relationships between any two chemicals and gene in a sentence is going to be none. And so we moved on to yet another type of formatting for our text-to-text problem, in which we first explicitly ask the model, is the relationship in the sentence between, and then we explicitly state one chemical and one gene. If the model answers yes, we then ask it to predict the relationship between that gene and that chemical. And then the only thing the model needs to output is the specific relationship of those two entities that we specified. And so here are the results comparing our baseline system with our text-to-text approach with only T5. We just didn't have time to produce results also with GPT, so our results are with T5. Our T5 model is generally worse than all of our baseline approaches, except for the baseline model BERT base. Our T5 model did perform on the development set, did outperform that baseline approach. I think with some our best performing models had like domain specific pre-training. So I think domain specific pre-training with the T5 model could definitely improve performance. And then also all of our vocabularies were BERT uncased, where it seems like BERT cased was much more successful. And then in addition, something that we didn't try with either of these models, I think perhaps a biomedical specific vocabulary would have also helped our models be more successful. So definitely I think there's so more work to be done before we can completely compare our baseline approach and our text-to-text approach. And then lastly, here are our results on our test results that we got back from the task organizers. Our best submission was an ensemble between our BERT base, BERT large, and biomegatron models, all with the masking approach that I talked about previously. And then our other submissions scored lower than those. We tried an ensemble between BioBERT and the T5 model as well. But yeah, our best submission was an ensemble between BERT base and biomegatron models. Okay, thank you. I'm happy to take any questions.
Okay, thank you. I believe Farouk is writing a question for you, Virginia. Let's give him a minute or so to finish writing. I don't know if there are other questions from the audience. Okay, if not, I will go ahead. I believe you participated in the task yesterday that involved the normalization, right?
Yeah.
Chemical normalization. And did you explore like combining the output of the normalization with your system to enrich the encoding information and maybe detect?
We didn't try that. Yeah, we just simply didn't have time. It took a lot of effort to like try and just get the systems up and running for T5 and GPT. So no, we didn't try that, unfortunately.
Okay. Okay. You already answered Farouk's question. So thank you, Virginia. We will go ahead with the next speaker. Thank you for your participation. Next one is Mehmet Fruz from the University of Delaware. So please go ahead.
Thank you very much. Can you see the slides?
Yes.
Thank you. Hello, everyone. I am Mehmet Efruz Karabulut, a PhD student from University of Delaware. Today, I'm going to discuss our participation in the DRAGPRO task. We hypothesize that an ensemble system can achieve superior performance if there is enough divergence among the assembled models. So our objective is to achieve divergence among the BERT-based models. So we propose an ensemble system including multiple BERT-based language models. We explore various architectures and pre-trained models for our goal. We choose 3 pre-trained models, namely BioBERT, PubMedBERT, and BioMelectraLarge. These models have different masking, vocabulary, and learning objective techniques, and BioMelectraLarge is a large-size model. We also explored different model architectures. We considered last layer of the CLS token, an LSTM layer, and an attention layer at the top level of BERT to aggregate the information in the overall sentence. Another dimension we investigated is class-weighted loss function to mitigate the class imbalance in the corpus, DRAGPRO corpus. Finally, we consider 2 different entity masking schemes. We were provided with a set of abstracts, entities, and relations. We use Stanza software to split the text into sentences. Then we created sentence instances. At each instance, we marked a single protein and a chemical, and we assigned this instance to one of the 13 relation types, or marked it as a negative if there's no relation between the chemical and the protein. Then we apply the entity masking in 2 different ways. In the left one, we anonymize the target entities. On the right one, we explicitly use the start and end entity markers. Then we feed these instance relation pairs into one of the BERT variants, as you see. Overall, we addressed the relation extraction problem as a multi-class classification problem. We considered two types of ensemble learning methods. First, we considered MLP as a meta-learning method. Specifically, we extract the last layer of CLS token from each fine-tuned model. For example, here we have 5 fine-tuned models, and we combine their outputs using an MLP. And secondly, we consider a majority voting technique, which selects relation types that gets the most votes out of 5 individual models. I would like to describe the overall training process. We submitted 5 rounds. For the first 2 rounds, we trained the 5 individual models in group A and B, respectively. We used the original training set to train the models and used the development set to train the ensemble models. And we used MLP to combine the output of the individual models. For round 3, we used the models in group B, but this time we combined the data and partition into the 5 different partitions, as you see at the left corner. For each partition, we obtain 5 models, like a group of 5 models, and we use a separate MLP for these 5 models to get the combined output. After that, we use majority voting to combine the outputs of 5 MLPs. For round 4, we use the single model. We repeat the same data partitioning scheme, but use a single model. For round 5, we again use the same large model, but we reserve all of our data to train this model. The purpose of the round 5 is to see the effect of the large model in the compared to ensemble models. Results on the test set demonstrate that we obtained the best result on the rounds 3 and 4. And interestingly, as you see in the round 5, the F1 score of the single large model is almost the same as the ensembles of rounds 1 and 2. And we also observed that the best score in rounds 3 and 4 is due to the increase in precision, but we lost some of the recall compared to round 1 and 2. And finally, the results on the individual relation types shows that we had obtained the best F1 performance in antagonist and inhibitor relation. And we also observed that these combined MLP and majority voting techniques have a uniform increase in F1 performance for almost all relation types. Thank you very much.
Okay, thank you. It was a great talk. We already have here Electra, right? We had people using BERT, Roberta, T5 GPT, and now you explore also the use of Electra. So we are having all the people here already. If there are no questions in the chat, I will go to the next question because the next talk, because we are a little bit behind the schedule.
Mm-hmm. Okay. Let me start the share.
So yeah, okay. No, there seems to be no question. If anyone wants to ask a question to the speakers, they provided their email so that you can email them. Thank you. Next speaker is the Toyota team, the Toyota Technical Institute team, and it's a talk given by Naoki Limuna and Masaki Asada. Please go ahead.
Can you see my slide?
Yes.
Thank you. Hello, I'm Naoki Numa from Toyota Technical Institute. I will be presenting drug-protein interaction extraction with external database with information. Our system tackled the drug plot task as a classification problem or relation within a single sentence. We use external knowledge from databases to get better relation representation than drug plot corpus alone. We consider two kinds of external knowledge. One is description and structure information of drugs and proteins. The other is distant supervision data. Furthermore, we ensemble the models from these different kinds of knowledge. First, we will explain the model using description information and structure information of drugs and proteins. We perform pre-processing that masks the drugs and protein mentions in input sentence. After pre-processing, the input sentence is encoded by BART to obtain vector representation. Then, in order to utilize the information in drug and protein database, we perform relaxed string matching to link the mention in input sentence and the database entries. We use UniProt for protein database and drug bank for drug database. After the linking, we use textual information and structural information of drug and protein in the database. Regarding the protein, we use the description, the textual information, and the amino acid sequence as structural information. Regarding the drug, we use description as textual information and smiles as structural information. The description information is encoded by BART and one fully connected layer. The structural information is encoded by character-based CNNs. In the case of proteins, the character embeddings are assigned the character representing each amino acid. And in case of drugs, the character embedding are assigned the character representing each atom and each bond. Finally, we concatenate the representation of input sentence and the representation of each information and calculate relation probabilities through FC layer and softmax layer. We average the probabilities when we use both description and structural information. Next, we will explain the model with distant supervision data. Distant supervision data is built by matching the relation tuples in drug bank to text. Each relation tuple consists of a drug, a protein, and an interaction type. We perform dictionary matching of drugs protein names to extracted named entity. We then map the drug bank interaction types to task relation types based on relation annotation guideline to obtain distant supervision data. Next, I explain the model and the training using distant and direct supervision data. The model is based on PubMed, but the model is first trained on distant supervision data, then it is trained on supervised drug plot corpus. As for development set, each description and structure information improves micro-averaged F-score, and the model using both information further improved F-score. The model with distant supervision data did not improve the F-score, but the ensemble of description and structure information and distant supervision data shows highest F-score. For test set, the model with description and structure information showed highest F-score. We propose two BART-based drug protein interaction extraction model using different kinds of external knowledge from databases. One model used description and structural information of drugs and protein, and the other model uses distant supervision data. We achieved 0.763 F-score on test set. That it is 0.143 points higher than participant mean score. example results show the importance of considering description and structural information about entities. As future work, we would like to investigate a better way to construct and utilize distance supervision data. And we also want to discover useful database information other than description and structural information. Thank you for your attention.
Okay, thank you, Naoki. We have one question in the chat from Luis, and it is the distance supervision data affected differently to the different relation types? And what about the entity descriptions?
Sorry.
Yeah, if the performance improved by using distance supervision data, changed depending on the entity type. For instance, for example, for agonist, distance supervision data does not mean anything because we already have many examples of agonist, or I believe that is the question.
Yes, the relation with the instance which has not enough data size, it is effective for instance supervision data is effective.
Okay, I think that yeah, that makes sense. So thank you for the impressive work and the talk and the results and everything. And we will go with the next speaker, which is Ed Drisilla El Alali from the Sidi Mohammed Ben Abdullah University in Morocco. So please go ahead.
Hello, do you see my presentation?
Yes.
Hello everyone, I'm Drissia El Alali. I'm a PhD student at Sidi Mohammed bin Abdullah University. I'm going to present our participation at drug pro track of BioCreative 7 with the work multitask transfer learning based method for extracting drug protein interactions. The drug pro track aims at predicting the chemical chain relations present in a set of permutations and abstracts. The dataset contains 5,000 documents, which were split into 3,500, 750, and 750 for training, development, and test tracks, respectively. The dataset defines 30 relation types. We formulate the relation extraction task as a sequence labeling problem. More specifically, we assume that the chemical entities are given, and we need to find their related gene entities and relation types by adopting the biosegment representation. Firstly, we generate the context related to each chemical entity by replacing its position with a label, which is made up of two parts, the boundary tag and the chemical type. This allows the model to benefit from the semantic information of the chemical entity. Then, we assign a tag to each token of the generated context. In addition to the label O, we define a new label which contains three parts, the boundary tag, the gene type, and the relation type. One of the biggest needs for a successful deep learning systems is to extremely access large amounts of labeled data. Multitask learning is proposed to overcome data sparsity by learning to jointly solve similar or related problems to produce a more generalized internal representation. In our participation, we explored the multitask deep neural network proposed by Liu et al. The model adopts a hard parameter chaining where the lower layers are shared across all tasks, while the top layers are specific for each task. The shared representation is obtained from pre-trained language model based on transformer architecture. We used two models, SkiBERT and PubMedBERT. Finally, for each task or dataset, a Fari-connected layer based on softmax function is used to generate task-specific representation. We used the stochastic gradient descent to learn the parameter of the MTL model. The explored MTL can make use of different datasets and different tasks. In our participation, we select 3 tasks with 9 datasets. Relation extraction task as sequence labeling problem with Drake prot, Kim prot, take and N2C2 datasets. The named entity recognition task with the BC2GM, BC5CDR, and NCBI datasets, and finally the text classification task with the I2B2 2010 and ADE datasets. When the learn model produces the sequences of the drag prot task, we extract all the related genes with the relation types for each chemical entity. If the gene entity is correctly identified irrespective of the relation type, then it takes the intellectual argument provided in the entity's goal set. We submitted 4 runs as the final submission. The first 2 runs adopt the relation extraction task as the sequence labeling with the underlying 4 datasets, where the first run has SkiBERT and the second run has PubMedBERT as the shared representation. The 2 last runs adopt all the tasks and the datasets, where the third run is trained with SkiBERT and the fourth one is trained with the PubMedBERT. Now the results, we observed that the highest overall performance is achieved by run 4. It means that multitask learning benefits from the information contained in additional tasks to improve the performance of the man drag prot task when learned jointly. Moreover, PubMedBERT performs better than SkiBERT. This indicates that the performance of the task heavily depends on the quality and the size of corpora on which the language model are pre-trained. In addition, all runs effectively extract all relation types with competitive results, expect agonist activator, agonist inhibitor, and the substrate products of relations. This is due to the fact that the number of these relations in the training set is very small compared to the other ones. Overall, the results show the effectiveness of multitask learning for extracting drug protein interactions. They also demonstrate the efficiency of incorporating pre-trained language model for capturing greater contextual information and improving the generalization performance of the task. In the future, we would like to conduct a systematic evaluation of other transfer learning based methods, such as Roberta, XNet, and so on, to study their effects on the overall performance of the drag prot task. We made the source code of our participation publicly available. Thank you for your attention.
Thank you for your great presentation, and also for the work and the proceedings and the system description paper, which was very interesting to read. If there are no questions in the chat, I will go with the next slide presentation, because as I said, we are a little bit behind on the schedule. So once again, thank you, and let's welcome the next speaker, that is the Dr. Lianxin Huang from the University of Texas Health Science Center. So please go ahead.
Hello, can you hear me?
Yes, and we see the slides perfectly.
Yes. Hello, I'm Lianxin Huang from the University of Texas Health Science Center at Houston. So in this presentation, I will be describing the prediction system developed by our team in UT Health for the drug prot track. So in this track, we use domain-specific transformer models for drug-protein relation extraction. For decades, network pharmacology, which is built upon drug-target associations, has been used to accelerate the process of drug discovery. It has been implemented in several topics, such as drug target prediction, side effect prediction, and drug repurposing. Currently, there are many drug target databases, such as DrugBank, TDD, KEGG, and CTD. However, in these databases, drugs mode of action is usually unknown or missing. We don't know if the drug inhibit or activate its target protein. In order to have a more precise drug target network that can help drug discovery, automated methods are needed to extract drug-protein relations from biomedical literature. In the drug pro task, there are 13 types of drug target relations. The main track consists of 15,000 abstracts, and the large-scale track has up to 2.4 million abstracts. Because the parameters of many deep learning methods are sensitive to the number of training data, we pull the training set and the development set together and then perform tenfold cross-validation, so that in each round there are 3.8 thousand abstracts for training. We used 5 domain-specific BERT-based models to predict the relations between drug and protein. PubMed BERT, BioBERT, BioM BERT, and BioNL BERT with 2 different mask input files. One differentiates the overlapping drug and protein entities, and the other ignores this situation. Based on these 5 BERT-based models, we also implement Ensemble Learning because we generated 10 models for each method during the tenfold cross-validation. We have 3 strategies to perform majority voting in the test set. Fold first, which combines the result from different fold first. Model first, which combines the result from different model first. And overall, which pull all the 50 results and perform majority voting. In the weighted majority voting, we also use the same strategies. And we give different weights for different interaction types according to the performance in the development set. We also implement staking by using the results from the 5 BERT-based models as inputs in each fold to train a decision tree classifier, and then perform majority voting to combine the result from different folds. So here shows the F1 score for the 5 BERT-based models and 3 ensemble learners under the tenfold cross-validation. It shows the weights majority voting is the best, and all 3 ensemble learners are better than any single BERT-based model. In the test set, weighted majority voting also shows the best performance among our 5 submissions for both main track and the large-scale track. So in summary, our results show that domain-specific transformer model can achieve reasonable scores. The F1 scores for both main track and the large-scale track are about 0.77. In addition, our results also show that ensemble modeling enhance the effectiveness of deep learning-based approaches. Thank you. Any questions?
Okay, thank you. It was great having you. Just one quick question, and we will go to the next speaker. You said that the weight majority voting ensemble got better result in development and test. This happened for all relation types, or that changed depending on the relation type?
Oh, that's a good question. Actually, we did not look into each entity type. In the training process, we only look at the overall performance. And actually, the weighted one and the unweighted one are very close because the performance for different entities are very close. So I think that the performance only have a little bit difference.
Mm-hmm. Okay, thank you for answering my question, and we will. I thank you for the work you did at the DRAC-PROT. We will proceed with Diana Sousa from La SIGE from Universidade de Lisboa, Portugal. Please go ahead, Diana. Sorry, I think you're muted.
Okay. Can you hear me now?
Yes.
Okay. And can you see my presentation?
Yes.
Okay, thank you. Hi, my name is Diana Souza, and I'm here to present my team / BioTM approach to the BioCreative 7 Track 1, whose goal was to text mine drug and chemical proteins interactions, and we did it using biomedical ontologies. Oh, sorry. So the greatest motivation of our methodology was the usage of external information. So instead of relying only on the training data, we also relied on entity information in the form of biomedical ontologies. And therefore, what we did was associate each entity in the training data with a term in the biomedical ontology and use the information about those entities to add extra knowledge to our overall system. We thought that using this external information would improve the overall results compared to just using a baseline deep learning system, such as the BLSTM or Albert's derivatives. And we had evidence to think that this would yield good results because our team already had created the Beyond system, which uses multiple biomedical ontologies to extract relations between biomedical entities and different biomedical entities. And that was tested on multiple data sets. So we thought that just adjusting the steps that we did for the other data sets will produce reasonable results. However, that wasn't quite as straightforward as we thought it would be, and we couldn't get from direct application or just minor adjustments with the Beyond system the results that we expected for the track. So yeah. So instead of going through our system and explaining all the different parts, I'm just going to focus on what I think makes us different from the other approaches and why we think that we could do better with the approach that we are proposing. So the first relevant thing is that instead of considering only the 14 provided labels we did in training and development data sets, we added an extra label, a label of no relation, because for our the test set background data sets that were provided to us.
In the academic living grade.
Sorry. Sorry.
Go ahead. I think somebody unmuted by mistake.
Okay, sorry. So the test and background data sets that were provided to us only had the entities mentioned and not the relations that we all should consider. So we had to teach our system, because that's what the system was expecting, what wasn't a relation. So instead of only having positive labels, we added the label that transmits the option of two entities being mentioned in the same sentence and not being related for all non-labeled co-occurring entities in the same sentences. Also, to add extra external knowledge that I mentioned previously, we linked all chemical drug entities to the chemical entities of biomedical interest, to the ChEBI ontology, and all gene protein entities to the gene ontology. This last one we did via secondary steps. Since we can't link them directly to an existing ontology, we link them to their most representative Go term within the gene ontology. And these terms describe gene and protein functions and not the entities themselves. Here you have a system overview where you have the several steps: pre-processing, training, post-processing stage. Our system was built using bidirectional long short-term memory networks. and incorporated word-to-vec, word embeddings, and made use of different combination of input channels to maximize performance. One of those channels is the ontology embedding layer that I mentioned previously. In this channel, we were considering a relation between entities if their ancestors already had an established connection. We reinforce the relation that we're trying to determine. So in this, as you can see in this example, if you have a possible relation between two entities, if their ancestors already had a relation, we reinforce the relation that we were considering. We also experimented with the use of class weights for some models in order to reflect the different ratio between labels, because we have labels that didn't have many expression. But our problems were mainly in the pre-processing stage, because our system will not allow for the vectorization of the sentence where the entities considered overlap. So when we have entities constituted of multiple tokens and these overlapped, we had to choose between vectorizing one entity or another, and that created loss of information in the pre-processing step. Also, this step was quite a slow process, because in the past we had dealt with significant smaller volumes of data, and we never had to optimize for larger volumes such as the provided data set. So it took too long to process all of the data, and we ran out of time to do all of the adjustments that we planned to do at the beginning of the task. Therefore, our post-processing stage focused on damaging control by recovering data that we had lost in the beginning of the pipeline. So we not only included relations that were not considered for the training, but also included relations that were considered false negatives, and for both we compare them against detected positive relations within the same document between the same entities, and simply assign the same label. However, not even that last stretch of post-processing rules could save our results. So as you can see by our table of results, compared to the average task metrics made available by the task organizers, we were quite low in the performance, with our system failing mostly in the labels that had the least training examples, as this slide shows. However, we also did not perform well on labels that had more training examples, such as product of, mainly because these were more complex and constituted of multiple tokens, and raised the issues that I talked previously. So to conclude, what we think will significantly improve our results is improving the pre-processing stage in terms.
Okay, I think we just lost Diana, right? It is not only me.
It's not just you.
Okay. okay. We will try to recover her afterwards, but okay, Diana, are you back?
Yes, sorry,
Yeah,
I don't know what happened.
Don't worry, go to the last two slides. I think
Okay.
are missing. And, yeah.
Are you seeing?
Yes.
Okay. Just to conclude, so we have to focus on improving the pre-processing stage, and also improving rules to capture specific data set specificities that we encountered along the way. But we ran out of time to do all of these stages, so we had to put our best results further, and they were not very good. Here you have my main contacts, so if you have any doubts or suggestions, we are very open to listen and answer them. So thank you, and sorry for.
No, thank you. I think many of the technologies or resources you use are very useful, and maybe combined with other approaches, they will obtain really good results. I believe for the inhibitor class, your results were higher than for the others, right?
Sorry. Yes, I think so.
Why do you think it is?
Actually, if I'm honest, we didn't have the time to really do a proper evaluation of our results. But I think it's because there are more training examples that are the same. So the same level is classified multiple times. And the structure of the sentence is very consistent along the documents.
Mm-hmm. Okay. So Well, thank you again. It was
Thank you.
good to see a different approach to the task. And our next speaker is Chu Yi Li, and it will be a video talk. So I will reproduce it, and then if you have questions, you will be able to go with the questions. So give me 1 second to share the screen, and we will proceed. Okay. Device. Share.
Hello, I'm
Okay.
Chu Yi Li, the speaker of the online introduction video. On behalf of TMU NLP team from the NLP lab of Taipei Medical University in Taipei, Taiwan. As you can see on the screen, our topic is identifying drug-chemical genes interaction in biomedical literature using the BERT-based ensemble learning approach from the BioCreative 2021 Drug Pro track. We all know accurate biomedical entity relation prediction is essential in numerous biomedical research fields, and due to the current global pandemic, it further triggered abundant studies that provide new biomedical research and knowledge. While biomedical literature accumulated at a record-breaking rate, it has become increasingly challenging to efficiently analyze drug-related information described in the scientific literature. Natural language processing method can provide efficient tool to detect crucial information regarding chemical entities and gene entity in a great deal of biomedical articles. As student doctors and data scientists at medical school, we are delighted to participate in this academically renowned BioCreative workshop. We evaluated our method with BioCreative 7 Track 1, which is published available on Drug Pro corpus that contain chemical and genetic entity annotations. Certain sentences that contain chemical and genetic entity relationship were classified into 13 types. The relationship distribution of trained and developed dataset is described as the data figure. Then, we constructed the distance mechanism and LLR-based trigger word weighting counter as the feature engineering method. For our implementation, we applied BERT with biomedical language representation to develop the relation extraction model. Finally, some submission we evaluated the result and adopted 3 or more models prediction through a voting mechanism to reach ensemble learning. In order to find out the proper pre-trained BERT model for the task, we applied hundreds of biomedical representation BERT model with or without feature engineering. We conducted experiments to evaluate the performance under a 5-fold cross-validation scheme and found that PodMed BERT is comparable with BioBERT and BlueBERT top others by a small margin. Finally, to take advantage of different BERT models, the first submission adopted these 3 models' prediction as an ensemble. And for the second submission, we introduced the distance mechanism with PodMed BERT and evaluate the result with and without distance feature. In the third implementation, we joined different batch size setting sorted models. Last but not least, we applied LLR log likelihood ratio to count the term weighting between trigger word and category. Due to the limitation of hardware equipment, we tried to submit 3 large-scale experiments that are the PodMed BERT model with and without distance mechanism and BioBERT model with distance feature. The final performance table is shown above, including the test dataset and large-scale dataset. The result has shown our 4 submission performance range from F1 score under 1% to 20% in terms of aspect of the test set. This performance of interaction identification is far from our validation experiment. We speculate that this is due to some under-detected error in our program, and the performance of the large-scale dataset range from 56.52 to 58.34% F1 score. In conclusion, we found PodMed BERT with distance mechanism achieved the best performance. As we know, we participate in this workshop today is attempt to do better entity relation extraction. In the presence of increasing amount of real-world data, An efficient interaction extraction model using with NLP method is bound to print out useful information hidden in an enormous amount of text. This work is worth achieving to have machines learn self-predicting on their own to help researchers conduct in more depth. Thank you very much for the privilege of presenting our work. I'm Speaker Chu-Yi Lee. We are TMU NLP from Taipei Medical University in Taipei, Taiwan.
Okay, so this was the video. It was really interesting to have also your team here, and from the Taipei University. And once again we are in the break time, so I don't know if there are questions from the audience. If not, I would like to thank you the participation and thank you for participating also in the large scale track, and because I mean the results were quite good at the large scale track, so thank you. And we will proceed with the next speaker. That is Denise Mejai from Catalytic DS, and I believe you will present in live, right?
I'll do my best to get it under the time limit. Let's see here.
Okay.
Can you see my slides now?
Yes.
And everybody can hear me. Oh, the bar is in the way of slideshow presentation mode.
We don't see the bar, Dennis.
Yeah, it is for me though. I can't click on present. Just a second. Yeah. Pardon me, I'm a bit of a Luddite when it comes to these beautiful pointy clicky things. There we go. Alrighty. As you said, I'm Dennis Mejai. I'll be presenting Catalytic's team submission to the Drug Prot Challenge, which we're calling a syntactically guided BIOL-STLM with BERT-derived word vectors. Just a general note on our approach. We're just doing NLP on a per sentence basis. We're not using knowledge from any ontologies, any data sets with drug or protein structures. And we're not doing any kind of reasoning on the whole abstract, which would be interesting, but that would require named entity resolution. So we're just, the only heuristic we use is that we restrict our predictions to same sentence interactions, which I think is in line with the annotated data set. Any of this, though, we speculate would improve performance. We submitted two systems, one sort of a strong baseline. We re-implemented BioBERT in PyTorch. Re-implementing it is pretty simple. It just has to do with masking the inputs, as I'll show in a minute. And this system was competitive on the ChemProt challenge, so we thought it would be an interesting baseline to compare against. And then we call it our experimental system, was a syntactically guided bidirectional LSTM, which basically walks through a parse tree between the protein and the drug and feeds that into a bidirectional LSTM to make a classification prediction. Both of these systems were trained using the Hugging Faces trainer class with early stopping, searching for hyperparameters in both cases, and also for system for LSTM configurations in the second system. And we selected a single system, a single instance of each. We didn't ensemble things, although that in retrospect, it looks like that might have been a good idea. We selected systems based on performance on a held out subset of the development set, which we selected using a group stratified partition, 20% partition of the development set. So this briefly is our baseline system, the BioBERT system using PubMed BERT as the underlying BERT model. We've seen this many times today. You basically mask the entire phrase for the chemical or drug and the gene, feed it through a BERT model, and then add a linear classification layer on top of the class token to predict one of the 13 interaction types or the null interaction type if there's none between those two. One thing we noticed though about BioBERT is as you get more distance, and here we're just measuring in characters, more distance grows, the distance grows between the drug and the protein or gene, the performance drops off. That's because BERT is not a syntactic model, even though it contains information that could be used to make syntactic predictions. It's not designed to capture long distance relationships reliably between terms. So as they grow more distant, of course, the predictions are going to become less reliable. And I don't have the statistics, but it looked like a lot of them, it was just saying there's nothing to see here, even though there might be an interaction between the protein and the drug. So the go-to way of capturing long distance relationships between terms and phrases is to use a syntactic parser. So what we did is we took the same underlying PubMed BERT model, we fed it through spacey transformers, which allows you to align the activations of the word piece tokens with actual syntactic tokens. And then using a spacey parse, we computed all paths between any token in the drug phrase and any token in the protein phrase, took the shortest path and walked along that path through the parse tree and enumerated those tokens into a sequence, which we fed through a bidirectional LSTM model. So there was the average token activations of the word piece tokens and a few parser-derived features. And then the BiLSTM has a classification layer on the final hidden layers of the forward and backward directions. And what you see here is that this model preserves the classification accuracy at the short distance, but also improves classification accuracy as the protein and the drug get more distant from one another in the sentence, which is what we were hoping for. And this is just classification accuracy, predicting one of the 13 interaction types or the null interaction. Here's our overall aggregate results. We've got accuracy, binary accuracy, which is just saying whether or not there's an interaction at all. And then the precision, recall, and F1 scores. And I'll just give the high level summary. We outperformed the BioBERT baseline in everything except recall. And we outperformed the BioCreative mean scores in everything but recall. There was no accuracy results reported there, so I can't say how it stacks up there. And this is probably because, parsers are brittle, and if you get the wrong patterns, if you don't get the same patterns you saw in training at test time, it's going to say there's no interaction. But if you do get the same patterns you saw at training time, it's going to be highly precise. Brief note about the fine-grained results. We don't do great on the low data interaction types. That's no surprise. So what we did is we plotted the F1, basically the precision recall in F1 on the held out dev test set, that's 20% of the development set, and just the F1 on the remainder of the development set, plotting it against training set size. And yeah, no surprise, the ones that have very low training set representation don't do well. There's a couple that outperformed expectations, those are the agonist and antagonist types. And when I looked into the data, basically 96 to 97% of the time, there was a term like agonizes or agonist or antagonizes in the sentence. So those are easy to predict. And the ones that underperform expectations, given the training set size, the two notable ones are inhibitor and indirect downregulator. And I think we had a participant from Florida that mentioned that those are even conflated in the annotation. So that's understandable. They're similar interaction types, so they're going to be conflated by the system. Also, looking at the examples, they're quite complicated. So just my subjective judgment. So things that we didn't do that would likely improve for performance, we'd like to update I failed to mention this, but we don't fine tune the underlying BERT model with the error gradients from the bidirectional LSTM. Doing so would probably improve performance. We'd like to do whole abstract reasoning. And what I mean by that is if you have an instance of a drug, an instance of a protein, and there's a very confident prediction that they have an interaction type because there's a good context in one sentence, you might want to propagate that throughout the abstract because as I understand the annotation guidelines did that, right? So even if there was no context to show in a certain sentence that in the title, for example, that this was an interaction of a certain type, they still annotated it that way. And then rules and maybe some other heuristics for low data interaction types like agonist inhibitor, which are at the same time very complex and very underrepresented in the training set. And I should add probably another bullet. We probably should ensemble our model, all of the models that we trained, and do majority voting or something of the sort. Thank you for your time. I'm open the floor to questions.
No, thank you, because the presentation was excellent. Also, the error analysis is very relevant, and yeah, it's very interesting for all the people here. I think for all the participants that also probably got similar issues than you. And if there are no questions, we are in a break time, so we will finish here the drag prod session. I want to thank you all the participants, all the attendees, and everybody involved here. And we will be back at 3:15, like in 6 minutes, 3:15 UTC time. So I welcome you to join in 6 minutes for the poster session. See you.
Hey, Lynette, can you hear me?
Yes, I can.
Sound clear? I can share for a second, but I think I should be good.
Okay, maybe we won't do it since they're already showing the yeah, slide. But I just want to make sure. I'm going to tell Chris, for some reason you're not on the list of people I can send chat to, so I'm going to make sure you get added to that list. But okay, good. Thank you.
Perfect. Thank you.
Maybe I'll take this opportunity to do a sound check. Lynette, this is Özlem.
Hi, Özlem. Great. Yes, I can hear you. Excellent. Thank you.
Awesome. Thank you. How are you?
Good, good. Enjoying this. So looking forward to
It's an excellent program. Thanks for putting it together. Really cool.
Yeah, it's most of the other organizers, but yes, I think it's been actually really good. So great. Talk to you later.
Perfect. Sure.
Hello, everyone. Let's start the poster session. It's difficult to have a poster session when all of us are online, but let's try to be able to create something doable and something that all of us could be interactive as much as possible. So I thought we would think of this as a poster visit, and as all of us now are taking a turn about the room and are looking at the posters together. So this kind of poster walk will contain 17 stops. We have some works that were selected from the poster submissions, and some works that were part of the tracks, were track submissions. Please note that for each poster, you will see a poster number, the title of the work, and the speaker name. If this poster is associated with the track, I added also the track number. And all of this information is to make it easier for people to ask questions. So during this trip, I will go through each of the videos. They are each 2 minutes long. And if you could, during this time, enter your comments or questions in the chat box or in the Q&A. We do have the poster presenters here present, so they can interact with you at the end. We have a few minutes at the end. But in order not to be confusing, let's use the poster number or some of this information so that to make this this to go smoothly. Okay, let's start. This is the first. Please, can you let me know if you are able to hear the videos? No? Okay. Chris, can I have some help?
You can either stop sharing, and then when you share again, you hit that bottom left share computer audio, or under your, yeah, okay. You gotta hit that checkbox on the bottom left. So as soon as you open share screen, you're gonna highlight the poster session, but then on the bottom left, there's a checkbox that says
Share sound.
Share computer sound, yes.
Okay, let's start again. So this is poster number 1, claim detection in biomedical Twitter posts by Amelie.
Everyone, my name is Amelie Wöhl. I'm a PhD student at the University of Stuttgart in Germany, and I'm here to tell you about some joint work with Roman Klinger, where we looked into how we can detect biomedical claims in Twitter posts. Now, social media platforms like Twitter are full of posts in which people share potentially very insightful experiences with their medical issues. And this information might actually not be available anywhere else. However, it can be highly unreliable, and this is why we need fact-checking. One essential prerequisite for fact-checking is claim detection, and this is why we decided to build a dataset that lets us explore this task. The dataset itself consists of biomedical tweets, which we manually annotated for both explicit and implicit claims. And I wanted to highlight 3 key insights from our research. First, when we looked at the data, we found that biomedical tweets are highly populated with claims, and we believe that this emphasizes the need for fact-checking in the setting. Second, in our experiments, we found that we can detect claimed tweets reasonably well. However, implicit claim tweets are much harder to detect than explicit ones. And finally, a cross-corpus experiment suggests that biomedical Twitter posts are particularly challenging as an environment for claim detection. So to conclude, we're excited to be able to share this first data set for this task, and we hope that it will enable the community in exploring argument mining and other fact-checking related tasks in this domain. The poster, the dataset, and our people is available in the video description, and I wanted to thank you all for watching. Bye!
Were you able to listen to this video?
Yes.
Okay, then let's move on. This is the second poster, visual exploration of randomized clinical trials for COVID-19. Abel Correa Diaz.
It was a little glitchy, Rosada, so if you have other applications or programs open, it might help if you I'm
Mm-hmm.
close going those. to present the tool we are developing for visual exploration of And it's very soft. You can bring your computer volume up. This work is part of my doctoral thesis. The initial interface presents a field formatted in a query term used to filter clinical trials. The query terms should refer to medications or adverse reactions. Let's try looking for ivermectin. After querying, the user is redirected to an exploratory view that presents a graph showing the treatments and the adverse reactions associated with the query terms. In the right corner, a panel gives the clinical trials filtered by the query and some information about them. A color scale is used to indicate the number of clinical trials retrieved. In parallel, we also present a numerical value next to the vertex in the graph. This visual encoding supports the following interaction idioms: hovering over the vertices to highlight the relationships between them, clicking on both sides vertices to filter the clinical trials, click on edge to retrieve the clinical trials associated with the relation. The audio dropped through that.
Hi, my name is Abel Correa Diaz. I am going to present the tool we are developing for visual exploration of randomized clinical trials for COVID-19. This work is part of my doctoral thesis. The initial interface presents a field formatted in a query term used to filter clinical trials. The query terms should refer to medications or adverse reactions. Let's try looking for ivermectin. After querying, the user is redirected to an exploratory view that presents a graph showing the treatments and the adverse reactions associated with the query terms. In the right corner, a panel gives the clinical trials filtered by the query and some information about them. A color scale is used to indicate the number of clinical trials retrieved. In parallel, we also present a numerical value next to the vertex in the graph. This visual encoding supports the following interaction idioms: hovering over the vertices to highlight the relationships between them, clicking on both sides vertices to filter the clinical trials, click on edge to retrieve the clinical trials associated with the relationship, clicking on the item panel to see the clinical trials on the clinicaltrials.gov website. This tool is under development, and we use the drug bank data and UMLS, Unified Medical Language System, to support the identification of treatments and adverse reactions in the clinical trials.
Introduce you to COVID-C, the scientific evidence explorer for COVID. COVID-C is a literature exploration tool that goes beyond basic search to allow users to dig into the deeper content of papers retrieved in response to a query through several complementary visualizations. Let's give it a whirl. We start by entering a query. The system responds by initiating a search in a search engine against a background collection. Here, we utilize the COVIDX neural information retrieval system built for COVID-19 articles. The user can filter the results using various familiar metadata features. Let's head over to the visualization dashboard. First, we see a visualization of relationships along the core PICO dimensions relevant to clinical research, namely population, intervention, and outcome. We have identified medical terminology in the articles that is associated with these aspects and found relations between them. The user can examine them to identify key relations of interest, select the band corresponding to those relations, and then add the document to their briefcase. Second, we provide a visualization of the topics that are represented in the document collection retrieved for the query. This can give the users a sense of the themes that are important in their subset. Finally, for each document, a concept cloud corresponding to the salient clinical terms that are found in the document is displayed. This helps the user to quickly get a sense of the core information in these articles. Once the user has added articles to their briefcase, they can be saved and exported for deeper reading or set as the active collection to enable iterative searching and exploration. We hope that that gives you a basic idea of COVID-C. Thanks.
Hello, my name is Robert Lieben, and I'll be talking with you about the long COVID collection. A significant percentage of COVID-19 survivors experience long-term symptoms that affect multiple body systems and impact the activities of daily living. However, long COVID is such a new and poorly understood condition that the terminology used in the literature is highly variable. This makes it difficult to query for long COVID articles, suggesting that a literature resource would be valuable. Lacking adequate training data to classify the articles directly, we can employ other relevant signals, such as a high-precision grammar for long COVID mentions, and automated taggers, which locate entities that are frequently mentioned in long COVID articles. Most powerfully, once we have some training data, we can use text classification tools such as LitSuggest. We integrated these relevant signals using data programming, which creates a generative classification model directly from the agreement rates between the signals. We apply this model within a human-in-the-loop framework, directing the human annotation effort to the most informative instances. As of the beginning of October 2021, our iterative process identified over 5,000 articles on long COVID. Comparing the collection to various PubMed queries underscores the difficulty of querying for these articles, with either limited results or too many false positives. Comparing the literature on long COVID to the literature on COVID-19 shows a significantly higher rate of several disorders, such as neurological disorders, cardiac conditions, and, interestingly, symptoms normally associated with COVID-19 itself. I'd like to thank my PI and co-authors, and especially the long COVID patient researcher advocates who have worked so hard to research their own condition. The long COVID collection is queryable at the Lit COVID portal and is updated weekly. We hope it can serve as a resource to help long haulers. Thank you.
Hello, I'm Sai Pradeep. I'm a scientist at TCS Life Science Research. I'll be presenting two approaches that we experimented for the track 5 of BioCreative 7 challenge on automated topic prediction of Lit COVID dataset. Both the approaches used pre-trained BioBERT model for multi-label assignment. As you can see in the slide, the first approach, what we refer as model 1, each article in the train and validation datasets were split into two sections, namely the abstract section and the remaining section. The abstract section contained only text from the abstract field, while the remaining section comprised of article title, the keywords, and journal type metadata fields. We used large BioBERT model pre-trained on MNLI corpus for this task. The BioBERT MNLI model was fine-tuned during the training phase on both abstract and remaining sections. This resulted in two separate fine-tuned models, one for each section. In the prediction phase, we performed an ensemble scoring of the predictions from both the fine-tuned models on the articles from the test data set. We experimented with three different ensemble approaches, namely simple average, weighted average, and maximum. The instance-based and the label-based validation F1 score slightly stored better performance for the maximum ensemble approach. Hence, we used this as our final score aggregation approach. The second approach, referred as Model 2, also splits the article content into two parts. Additionally, it performs NER on the abstract and the title text. Specifically in the second approach, we repurposed our text mining framework Priority to perform NER covering 27 different entity types, such as genes, proteins, and non-biomedical entity types, such as demographics, non-pharma interventions, etc. These annotations were then masked by replacing tagged entity with entity type tokens. The training and prediction phases continued to be similar like the first approach. In this slide, we present the results of both approaches. Model 1 showed better performance than the Model 2 and had a better performance than the baseline MLNet provided by the organizers. When benchmarked against the 80 team submissions for this challenge, the label-based macro F1 scores of our Model 1 was very close to the median score, while the instance-based F1 scores were very close to the mean F1 score. I thank the challenge organizers for giving me the opportunity to present our work today. Thank you.
Our paper, Biomedical Relation Extraction, Hybrid Approaches by Oner Kara, Fei Chen, Tommy Jenkins, Daniel Hug, Sajida Safari, and Seth Berger. So this is our abstract. So basically our plan was a cost-effective hybrid architecture for entity relation biomedical extraction. We used transform and attention-based models, as are all the rage. And then due to the scarcity of the data, we use synthetic data generation by using GPT-3. And I'm going to show you, so these are the models that we used. We used 6 models: BioLectra, PubMed BERT, SciBERT, Clinical BERT, and BlueBERT. You can take a look at the statistics here. But as you can see, BioLectra performed the best. And on average, the results using GPT-3 generated data achieved improved F1 scores from around +1 to +5. The original relation extraction scores that we got with the given data were around 75, and we were able to improve that to on average around 76 to 80. And our NER scores went up as well. In the future, we plan to implement knowledge graphs. This will help us make better predictions and reinforce the information retrieval from unstructured text. We look forward to presenting future research, and we hope you like it.
Hi, I'm Carol Anderson, and this is work that I did along with my coworkers at NVIDIA, Bo Liu, Anis Abedin, Hucheng Shin, and Virginia Adams. The goal of Track 3 was to extract mentions of medications and supplements from tweets in English from pregnant users. We approached this as a standard token classification problem with 3 labels: B drug, I drug, and O. We pre-processed the data using the standard spacey English tokenizer. We also added a few custom tokens to the tokenizer to ensure that they were split apart from surrounding text. For example, in the hashtag Concerta problems, this allowed us to give different token labels to Concerta and problems. We used NVIDIA's open source NEMO library for training. All of the pre-trained model checkpoints we used are freely available either from NVIDIA or Hugging Face. The models we fine-tuned are shown here, along with their performance on the challenge dev set. In every case, we added a token classification head consisting of 1 feed-forward layer. Megatron BERT is a 345 million parameter BERT-style model pre-trained on general domain text. We used it with either an uncased or cased vocabulary. The BioMegatron models have the same architecture, but were pre-trained on PubMed. We also used Roberta Large and BERT Tweet Large, which has the same architecture as Roberta, but was pre-trained on tweets. Our best single model was Megatron with the uncased vocabulary. We also made an ensemble of the 5 models highlighted in yellow and achieved even higher scores. For our official submissions, we used the same ensemble I just described, as well as another one consisting of 5 Megatron models trained on different splits of the combined training and dev sets. The Megatron-only ensemble outperformed the ensemble of 5 different models. In summary, we achieved good results with no handcrafted features aside from a minor customization of the tokenizer used for pre-processing. Our best performing models were pre-trained on general domain text, and we achieved the best accuracy by combining multiple models as an ensemble. Thank you for your attention.
Hi everyone, we're Team FSU 2021 from Florida State University. My name is Qing Han. The goal of Track 3 is to perform named entity recognition for medication mentions for tweets. Main challenges include non-standard expressions, extreme imbalanced classes, and lack of context information. We first conduct pre-processing step to clean out non-English and special characters. We chose PubMedBird as our baseline model, which had domain-specific pre-training from scratch and has achieved state-of-art performance. In addressing the main challenges, we considered 3 data augmentation strategies. 1. Augment by replacing original true entity with a randomly chosen medication from the golden pool. This strategy is relatively safe as it uses only the true entities. 2. Augment by replacing original true entity with a random string. This strategy is more aggressive by forcing the model to learn about context by introducing new names the pre-trained model has never seen before. 3. Augment by dropping a randomly selected word which is not or not belongs to a true entity. This strategy introduces more diversity into the context itself, which matches exactly the characteristics of tweets. In addition to augmentation of the original dataset, we also try to add more training data by using certain search terms to scrape more tweets. The result shows that the new tweets could significantly help in recognition of more entities so that the false negative cases could be largely reduced. However, this comes with the price of more false positive cases. As a conclusion, our best performing classifier utilizes the PubMedBird full-text pre-trained model and fine-tuned with the training datasets and their augmented datasets, plus the original SMM4H18 datasets. The augmented datasets were generated by 2 strategies combined. It turns out that our model achieved an F1 score, which is substantially higher than the mean of all submissions. I hope you're enjoying this video. Thank you very much for your listening.
Working with the Twitter data used in this challenge is not straightforward for 2 main reasons. The data is highly imbalanced, and the text is highly unique with a particular structure, style, length, and vocabulary. In this work, we have tried to address the class imbalance problem by data augmentation and the unique Twitter language characteristics by using 3 language models trained on tweets, Twitter Roberta and 2 variants of BirdTweet. We developed 2 different pipelines to fine-tune these models on the named entity recognition task using data from the BioCreative challenge. In both pipelines, we pre-trained the models on the SMM4H18 dataset. The first pipeline used the challenge training data augmented by upsampling tweets that contain drug names. The second pipeline augmented the tweets that contain drug names by tweet concatenation, tweet paraphrasing, drug name replacement, and upsampling. In this pipeline, we created 6 different models trained on random subsets of the training data, and then we aggregated the individual predictions by averaging. We used an ensemble approach to make the final predictions on the test data based on the predictions from the 3 individual models. Our objective function was the overlapping F1 score. Our model performed better than the average submission in the competition in all 6 metrics, and it performed better than the baseline Kusuri models in the overlapping F1 score. The results on the strict metrics were further improved by hashtag removal. Most of the false positives were a result of annotation errors, and most of the false negatives were due to failure to identify medication names that were not in the training dataset. In conclusion, we showed that using data augmentation to address class imbalance and Twitter-specific language models to address the unique characteristics of Twitter language were powerful approaches to process Twitter data for the named entity recognition task.
Hello everyone. We are Team Donut NLP from NLP Lab, Taipei Medical University. This is speaker Yuwen Qiu. As you can see, BERT-based ensemble learning is the spotlight of our methods. Manual annotation of chemical entities bring error from fatigue and also time-consuming. Therefore, the motivation of improvement led us desire to build a system to do recognition and normalization automatically. To achieve the goal, we first tried all BioBird models in Hugging Face, managed to find the most suitable one, and then we did ensemble learning on the best performance model of certain epoch in every fold when we training with K4 validation. Moreover, we expanded the dataset with 2 datasets of BioCreative before. As regards to the model itself, we had tried applied machine learning methods. After experiments, BERT stand out from all model architecture we had tried. BERT perform the best might be its encoder is very suitable for natural language understanding tasks, which is similar to our task. The results show Sultan, round 1, performed the best in normalization. Round 2 then performed the best in recognition with its method we composed of Sultan, PubMed BERT, and fine-tune PubMed BERT. Finally, in the first part, chemical mention recognition, the results of our experiment seems to be great. We got 85 and 92% F1 score in strict and approximate metric separately. The best performed BERT pre-trained model we chose was by Sultan, and it is of Electra architecture with Ensemble Learning. As for the second part, chemical normalization to mesh IDs, we got 81 and 80% F1 score in strict and approximate metric separately. We felt good for this result. Dynamic programming-based methods is our main architecture. It contains edit distance method, which is very useful for normalization, and also we expanded knowledge database every round, made our system faster and more accurate. Finally, we have some conclusion to tell. 1. In this task, models pre-trained by Sultan and DMSI lab performed the better, sometimes equally matched. 2. Ensemble Learning and edit distance did bring us better performance in this test. The next one, corpus expanding, did not always bring better results. That's all. Thanks for your listening.
Hi, I'm Robert Bevan. I work as a data scientist at the Medicines Discovery Catapult in the UK, and I'm here to present our submission to the NLM Chem Track Challenge. In our entry, we focused on the PubMed BERT transformer model, which is a BERT model trained from scratch using PubMed abstracts and PubMed central articles. First, we fine-tuned a single PubMed BERT model using the NLM Chem dataset. We then wanted to see if we could improve its performance using additional training data, namely the CDR and Chem DNER datasets. Each dataset has its own set of annotation guidelines, so it's impractical to combine them into a single dataset. We decided to try training separate models using each dataset, and then train a stacking model to combine their outputs. We wanted to see if the model could learn to map the different label types to the new dataset, and leverage the additional training data to improve performance. The stacking model didn't do any better than the single PubMed BERT model fine-tuned using the NLM Chem dataset, so we used a single model in the final evaluation. The NLM Chem evaluation set contains many long passages. PubMed BERT can handle sequences of up to 512 tokens or word pieces, so in order to process long examples, we applied the model in a strided fashion and averaged the outputs. The table shows our model outperformed the baseline by a fair margin. We applied a sieve-based normalization approach in a similar manner to the baseline. First, we normalized each of the terms contained in the mesh database by lowercasing, removing white space, and replacing Greek characters with their English spellings. We then defined a set of string manipulation and substitution methods to be used in the normalization sieve. The string manipulation methods included stemming and non-alphanumeric character removal, and the string substitution methods included abbreviation expansion using AB3P and similar entity substitution using biowordvec embeddings. The similar entity substitution approach works as follows. Given an entity, the 10 most similar biowordvec strings according to cosine similarity are retrieved. Strings with a similarity score below some threshold are discarded. The remaining strings are then resolved to mesh codes where possible, and the final mesh code is determined by majority vote. We also made use of several synonym data sources, namely KEBI, UMLS, NCI Thesaurus, UNII, and PubChem. Our approach performed slightly better than the baseline in the strict evaluation, but we think this is probably due to the significantly improved entity recognition performance rather than an improved normalization procedure. We can see from the ablation study that the additional data sources were the most important component, and that the abbreviation expansion and similar entity matching components had little, if any, impact. For the indexing task, we trained a logistic regression model to predict whether or not each identified mesh code belongs in the index. We used the following features: mention count, normalized mention count, the number of passages the code appeared in, the number of passages broken down by passage type, for example, the number of times it appeared in the abstract, and the mesh code. Our system was more precise than the baseline system, but with much lower recall and a lower F1 score.
Hello everyone, I'm Jin Hang from the Hong Kong Polytechnic University. Today I'd like to share with you our past work at the BioCreative 7 late COVID track, which was an ensemble learning method for the COVID-19 multi-level classification problem. In this presentation, the main contents includes the ensemble learning method and the experimental results. Our basic idea to deal with the multi-level classification is to leverage the ensemble learning method. Particularly, we propose to leverage multiple state-of-the-art pre-trained models, and we take each model as a single weak classifier. We train and fine-tuned these classifiers and ensemble them together to acquire a much stronger classifier to get the final predictions for the late COVID track. Specifically, we leverage 4 variants of the BERT-based model, which are BioBERT-based, BioBERT large, PubMed BERT, COVID BERT. And at the same time, we also leverage 2 variants of the Electra-based model, which are BioElectra and Biomedical Electra. We also leverage another biomedical Robota pre-trained model. In addition to the ensemble learning method, we also proposed to leverage the additional biomedical knowledge to further improve the final performance of the late COVID prediction. In particular, we propose to leverage the keywords, the journal information, the MASH headings, as well as the original document text, including the titles and abstracts. This figure just shows the input format of our method. We concatenate all the additional biomedical knowledge with the original document text, and we take this new text as our input, and we feed this input to our models. During the competition, we totally submitted 5 different predictions according to different ensemble policy. And this table just lists the final performance on the test dataset. From this table, we could find that our submission 3 and our submission 5 acquired the best performance at the macro F-score, and example-based F-score respectively, which just illustrating the effectiveness of our proposed method. Here are some related references, and that's all. Thanks for your attention.
Hi, we're Team FSU 2021. My name is Shubal Tian. I'm happy to talk about our participation in the lead COVID check of Creative 7. This check is a multi-label classification task for automated topic annotation of COVID-19 literature. There are 3 data sets for this task, a training set and a development set for model development, and a test set for evaluation. The key challenges of this task include the complexity of assigning multiple labels to an article, the large variation in article lengths, missing titles or abstracts, and imbalance in topic distributions. To tackle these challenges, we use PubMed BERT as encoder and developed and trained several BERT-based models with different strategies. The first model directly built classifiers on top of PubMed BERT. The second model applied an attention computation between PubMed BERT and the classifiers. The third model is multi-instance learning to adjust the issues of large variation in article lengths. The fourth model uses a focal loss function to deal with imbalanced topic distributions. The last model uses average method for ensemble of different models. Test results showed that our approaches were able to achieve satisfactory performance, with the best results achieved by the ensemble method, whose F1 score is significantly better than the baseline and average of all submissions.
Hello everyone. We hereby describe our submission to the Biocreative Share task, which is a neural document classification model that uses an intermediate cipher layer for document representation. And here are the names of the team members who participated in the task. So we reused the model on multi-label patent classification that we published in ECI 2021. And the addition that we did as part of the shared task is we incorporated the metadata information. In our analysis, we found that author-provided keywords are most informative metadata field. On the figure on the right side shows the model architecture for the best performing submission. So we have titled an abstract and also provide keyword as two inputs, which are converted into a text sequence and passed through a cybert layer. And each of them is converted into embedding, which is concatenated to generate a document representation. The document representation is then provided as input to each of the tasks. Which makes a prediction whether a given document is relevant to a label or not. On seeing the results, we find that the best performing submission is much better than the baseline for the task, and also it's much better than the mean of the submission statistics. Also, our submission results are at par with the Q3 or the third quintile of the submitted results, which shows that we are approximately better than 75% of all of the submissions in the task. So with this, we show that that our system, which was originally developed for multi-label patent classification, is applicable for other domains as well. Thank you very much.
Hello, I'm Tomoki Tsujimura from Toyota Technological Institute. We studied track 2 tasks with BERT-based neural models. At the NER task, we used a simple BERT-based sequential tagging model. We left studying the NER task deeper, instead spent more time for the linking task. Our linking model is a single neural classifier. We tackle the linking task as a classification problem. In other words, our model outputs the probability distribution for all mesh IDs on the thesaurus. Another characteristic of our model is using cosine similarity-based output layer like cosine phase. The input is subwords of the mention without any context. We build the training instances from not only the original corpus, but also from the synonyms on the mesh thesaurus. We also tried using BC5 dataset as the additional training data, but it didn't make a big difference. At the post-processing, we used the abbreviation solvers. As a result, our model got a little better scores than the median F value. For the indexing task, we tried to build a TF-IDF model and a neural bag of sentences model that is similar to the one used in distant supervised relation extraction task. This model is very sensitive as error propagation. If the predictions are made from the goals spans and IDs, got better results than TF-IDF model, but on the pipeline setting, much worse than the TF-IDF. One possible solution is using the training instances built from pipeline stages that we couldn't try due to the time limitation. As a conclusion, we built neural NER linking and indexing models as well as a TF-IDF indexing model. Thank you.
Hi everyone, my name is Rui, and I'm presenting the work we developed for the drug-prod track of BioCreative. The goal of the drug-prod task was to develop a system for extracting relations between chemicals and proteins in PubMed abstracts. Here we see a sample sentence with activation and inhibition interactions between some chemicals and proteins. For this task, 13 relation types were defined. The drug-prod dataset was composed by PubMed abstracts, annotated entities, and relations. The drug-prod dataset was split into 3 subsets. The training and development subsets were used for developing our model, while the test subset was used for official evaluation. Regarding the distribution of relations, we see these are highly unbalanced. The inhibitor interaction is the most frequent one, and there are some interactions that are almost non-existent. The first step of our system consists in splitting the documents into sentences. Then we considered as candidates for the relation extraction all the chemical protein pairs within the same sentence, ignoring pairs with overlapping entities. The next step is about encoding the text. For that, we use the PubMed-BERT transformer-based model. We perform tokenization, dummification, where we replace the chemical and protein mentions by dummy tokens, padding or truncation since we set a maximum input sentence length, and finally, from the BERT output, we concatenate the CLES and the dummy token representations. For the classifier model, we test three approaches that we denote here as base, last layer, and attention. In the base approach, the classifier corresponds to a two-layer neural network followed by a softmax or sigmoid activation function for single-level or multi-level predictions. As you see here, the input corresponds to a sentence and a candidate chemical protein pair. It is tokenized and the entities are replaced by dummy tokens, and from PubMed-BERT, we use the CLES and the dummy token representations as the input for the two-layer neural network. Regarding the last layer approach, the only difference is that we additionally train the last layer of the transformer model. The final approach, denoted attention, consists in adding a multi-add attention mechanism. First, we created a relation class embedding representations using textual definitions from the annotation guidelines. Then, we considered the class representations as queries and the sentence output from BERT as key and value. The intuition behind this mechanism is to give the model an idea of what type of information we are looking for in each relation class. The output representation obtained from the attention mechanism was then concatenated with the CLES and dummy token representations. This final representation is then forwarded to the neural network classifier. Other details about our system are, for instance, we perform a balancing between precision and recall to maximize F1 score by selecting an optimal threshold to predict a relation class as positive. Also, we average the 4 models predictions using different random initializations, which consistently allow to improve our results. In this table, you see the configuration of our 5 submitted runs and the respective official results. The base approach attained the 0.60 F1 score corresponding to our lowest result. The attention approach using relation class representations proved valuable by surpassing our base approach by 6 percentage points. However, we observed that training the last layer of BERT was way more beneficial, achieving our best results, being 9 percentage points above the average from the submissions of all teams. As future work, we intend to perform dependency parsing, evaluate the use of entity markers, explore the use of other tools and models, and perform multitask learning. Finally, we'd like to thank the BioCreative organizers for having these challenges. And with this, I end my presentation. Thank you for your attention.
Hi, everyone. So this is our last stop. It's poster number 17. And according to our program, we are scheduled to start it up with our panel soon. I do not think we will have time for question answering, but I invite all of you to use the chat for that. And the presenters are behind their screens. Please utilize the chat for this continuation. I will run this last video and will pass on to Martin. Thank you.
Hi everyone, my name is Jihad Tahdouh and I am a PhD student at University of Helsinki. Today I'm going to speak about our model called RBERT-CNN, which aims to extract drug-target interactions from biomedical literature. So first I'm going to speak about drug-target interactions, and after that about our model, and finally the results and discussion. Knowledge about drug-target interactions are critical for drug discovery and drug repurposing. Drug Product Challenge aims to promote the development and evaluation of systems that can automatically extract the relations between chemical and protein entities. In this paper, we are presenting our model called RBERT-CNN. We will speak later on about it. So first, we start with the datasets. As you see here in this table, we have the training dataset, development dataset, and the test datasets. Also, we have the chemical protein entities. In addition to that, we have the positive relations. We have decided in this study to ignore agonist activator, agonist inhibitor, and substrate product of relations since we have very few samples for each relation. So pre-processing is a critical step in text mining before feeding the text to the model, and we have used an LTK package in Python. First, we replaced the tab delimiter between title and abstract with a single space, split the raw documents into different sentences. We ended up with this format. So we have the as symbol, means the start of the sentence, and we assign special tags for chemical and protein entities, and this means the end of the sentence. And also we have created a new label called other for entities without any relation. Our model is basically an extension of three models. Biomed Reporter Base is a language model built on Reporter Base proposed by Facebook, with an additional pre-training of 12.5 thousand steps. It was trained on more scientific papers, both abstract and full text, taken from Semantic Scholar. The second model called RPERT, which was proposed in the article, enriching a pre-trained language model with entity information for relation classification. In this article, the authors involve information from the target entities through the BERT architecture. The last model is called BERT C and N, proposed at Semantic Evaluation 2020, Task 12. So basically, they take the last 4 layers of BERT model and feed it to convolutional networks. Here we have our model, 3 components. The first one is first entity embeddings. We take the average and feed it to fully connected layer, same to the second entity. And the third component is the last 4 layers of Biomed Report Base model. Feed it to 3 convolutional networks with a 3 filter size, and each one followed by rectified linear unit, and after that max pool over time. We concatenate the results, feed it to fully connected layer, and after that we concatenate the whole results here and apply the cross entropy loss to get the classification task. We achieve 56% F1 microscore over the drug prot test data and 63 over chem prot test data, and we are currently improving our model. Thank you so much.
So welcome to the panel on challenges in mining adverse drug reactions. And I just wanted to briefly introduce the panelists and the panel. So Martin Kraulinger will be leading off and chairing the panel. And what we're going to do is each panelist will have a short presentation, 5 to 7 minutes, and then we're going to go into a series of questions. So I would encourage you to keep the questions in mind as we're going through. So what are the critical applications for text mining of adverse drug reactions? What are the sources of mining adverse drug reactions? Because there are many sources, and we'll hear about a number of them in these quick presentations. And what challenge evaluations do we need to drive progress in this area? And I think this is going to be a very exciting panel. So with that, let me give you a very brief introduction of Martin Kraulinger, who really doesn't need any introduction. I think you've all hopefully been watching, for example, the track presentations this morning. He is, he is the head of the text mining unit at the Barcelona Supercomputing Center and former head of the biological text mining unit at the Spanish National Cancer Research Center, CNIO. And he is a veteran of, I think, all of the biocreatives and has been really a driving force in biocreative. So with that, Martin, I will turn it over to you.
So thanks a lot, Lynette. I hope you can hear me. Please just quickly confirm.
Yes, we can hear you.
Perfect. So I would like to introduce a little the motivation on why we have chosen a panel on adverse drug reactions at the BioCreative 7. Because obviously there was no shared task on adverse drug reaction so far in BioCreative. But I would like to highlight that we did have several shared tasks at BioCreative related to the detection of chemical entities and drugs from various kinds of content. So we had actually back in BioCreative, I think it was 4, a task specifically devoted to the detection of chemicals and drugs in PubMed abstracts. And we'll come back to this track later on. We did have a track on detection of chemical entities and drugs from patents, medicinal chemistry patents. And part of the motivation on the patent task also has to do with the detection of adverse drug reactions or adverse reactions from other kinds of content. We did have shared tasks also on recognition of entities together with chemicals, so interactions between chemicals and other entities, other biomolecules, mainly genes and proteins. And basically, you had several talks today on the drug-product relation extraction task. And here I have to say that this task might not seem to have a direct connection to adverse drug reactions, but if you look at the molecular aspects behind some of these off-target interactions or drug metabolisms causing, for instance, adverse reactions, there is obviously also a connection more at the molecular biology or the molecular level in terms of adverse reactions or interactions between drugs and other kinds of bioentities. And we had a task on detection of drugs and chemicals from full text articles. So there's obviously the basis for finding or mining adverse drug reactions already, posed in previous BioCreative editions. So if you go back to the very first one, the chemical recognition in PubMed abstracts, the Kempner track, the motivation on why we actually posed this track quite some years ago was because we were involved in a project, a European project on toxicology, in this case with pharma. The purpose of this track was focusing or trying to develop tools for detecting organ level toxicity related to chemicals in preclinical studies, but also to detect this kind of information from literature, from scientific papers. And what we actually discovered back then is that there was a need to develop very robust and also to evaluate systems for finding chemicals and drugs in the literature in the very first place. That's why we posed this track. Finding or mining adverse reactions from literature and also from other kinds of sources is really very complex. So you might have very direct associations between a drug and an adverse effect description, but these are quite rare, and you will find many, let's say, associations of adverse drug reactions which are a little more indirect, which might have to do with the metabolism of these drugs, which might have to do with some alteration of biomarkers, which are able to monitor organ dysfunction. So it's quite complex to find this kind of information in the literature. And also, there's a lot of content on adverse drug reactions, which is not in English. So if you go into electronic health records or case reports, there's a lot of data and content which is important, which might not be in English or which might not be even literature or electronic health records. And we were starting to do some annotations and some corpus on adverse drug reactions from electronic health records, but in data in Spanish, although the examples are in English. So obviously there might be very, let's say, direct associations between a disease or adverse reaction, adverse event and the drug. But these kind of, let's say, very explicit relationships, which you could tackle with a classical relation extraction task, are not that frequent. And you will find many cases where, like in this example, it might be also, let's say, modeled more than a relation extraction task, but as a classification of drug mentions according to the context. So whether in the context there's some adverse drug reaction described. So you could see a model that also, let's say, a classification task, not only a relation extraction. And the difficulty here as well is that sometimes you really need to have some more insights on kind of clinical attributes which are relevant to actually determine or to model or to exploit adverse drug reactions in a clinical or even in a biomedical setting. So I think this is more like as a brainstorming in the very beginning. So finding or mining adverse drug reactions obviously is a very complex topic. There are lots of different kinds of content which might be of relevance: literature, electronic health records, and social media. We will see this later on. And there are also different ways on modeling adverse drug reaction from the text mining perspective, from very classical relation extraction approaches, with the difficulty to actually have manually annotated adverse events in complex data like electronic health records or literature. Or you can model this also as a sort of classification task of entities according to whether there's some adverse reaction described in the context of the mention of this particular entity. So basically, this was a little my motivation in terms of the biocreative organizers, that we did quite some groundbreaking work on finding these drug and chemicals in different kinds of content. And we did some tracks on relation extraction, which involved chemicals and drugs. But there's clearly some need to go beyond this in terms of maybe changing how we could model this kind of task, and also how could we contribute or what could be done in terms of posing challenges and new drugs and generating label data collections, which could be shared by the community.
Thank you, Martin. So our next speaker, our next panelist will be Commander Monica Munoz. She is the Deputy Director of the Division of Pharmacovigilance in the Office of Surveillance and Epidemiology within the FDA's Center for Drug Evaluation and Research. And in this role, she provides scientific oversight for pharmacovigilance activities and initiatives. So thank you very much, Dr. Munoz, for joining us.
Can you see my slides?
Yes.
All right, perfect. Well, thanks for the introduction and for the invitation. It's really a privilege to get insights from the experts participating in this workshop. As a context for today's discussion on challenges associated with text mining ADRs, I thought it would be helpful to provide an overview of FDA's drug surveillance activities and describe a few examples where we've explored text mining. And this overview is certainly not intended to represent all potentially useful applications. The FDA's Center for Drug Evaluation and Research is responsible for conducting surveillance on all approved drug and therapeutic biologic products, thousands of products. So pharmacovigilance activities begin pre-approval. They continue throughout the life cycle of a drug. And our approach to surveillance is very multidisciplinary, and multiple data sources need to be integrated to inform decision-making. And because we're responsible for surveilling pretty much everything that touches the market, FDA takes a risk-based approach to surveillance, meaning we generally focus on products where less is known about their safety. We'll prioritize the evaluation of risks that can significantly impact the risk-benefit balance of products. And our priorities can change over time as drug knowledge accumulates. The signal management itself refers to all the activities that revolve around a potential safety concern. This framework starts with signal identification activities. And for FDA, this phase consists of both our ongoing surveillance activities, which include screening FDA's adverse event reporting system, the literature, and periodic safety reports submitted by sponsors or applicants of products. The safety concerns can also arise from our review and awareness of any other source, such as post-marketing studies, inspection data, social media, really any piece of data. The signals that arise from any source move to a signal refinement phase. This is where we consider preliminary findings on the causal relationship between the product and the safety concern and the potential public health impact to inform the triage and prioritization of signals that we're going to evaluate. The signals that represent potential risks are then formally evaluated in this evaluation phase. Here, teams evaluate the issue and any relevant data sources. And based on the evidence, the agency will take action, which may include further assessment, communication, and other risk minimization actions in accordance with the importance of the risk. So we look towards text mining applications to help improve both the efficiency, meaning how long does it take for us to identify, evaluate, and act on safety issues, and the scientific validity of our work. Are we making the best decisions based on the totality of the data? This includes, of course, the extraction and organization of adverse events from various clinical texts, but also the important attributes connected to those adverse events. FDA also needs to maintain awareness of technologies that may be used in regulatory submissions like adverse event submissions. So I'll highlight a few examples of text mining projects with FDA investigators connected to the signal management framework. FAIRS, our adverse event reporting system, currently receives over 2 million adverse event reports annually. And these reports are coded in MEDRA terminology, either by industry or FDA. FDA codes reports that are received directly from the public through our MedWatch program, in which the coding of MEDRA preferred terms comes primarily from unstructured text that looks like this. So there have been efforts to facilitate extracting AEs and related information from narratives over the years. As an example, we used unstructured narratives to supplement coded demographic information that connects to each adverse event report, which is really important for us to enable reviewers to retrieve specific reports when searching the database. Demographics, in addition to adverse events, there are also basic attributes incorporated into our data mining algorithms we use for signal detection. In the signal identification phase, key question is the adverse event already described in the prescribing information or labeling, and where is it described? We refer to this as the labeledness or expectedness. Because FDA reviewers are surveilling hundreds of products and safety-related labeling changes occur frequently, reviewers routinely need to pull up that current labeling to make expectedness determinations. So there have certainly been efforts in this area to develop tools to translate labels into MEDRA terminology, so it could be used to automate those determinations of expectedness. More recently, MITRE and the FDA shared an organized task, AD eval, to determine whether the performance of algorithms might be good enough for real-world use in our pharmacovigilance applications. And many of these tools perform quite well, supporting further implementation and decision support workflows. The evaluation phase is where reviewers take focused, deep dives into the data to assess things like causality. In spontaneous reporting systems, this means assessing the unstructured narrative, the underlying story behind what was reported. So there's certainly been text mining efforts that aim to extract different features from the narratives to support case review. These papers are older examples from FAIRS, the vaccine counterpart to FAIRS. And in our Sentinel system, which includes medical claims and source data, FDA has completed projects and machine learning to improve identification of interest. Last example, and some connected papers to it, took a look at anaphylaxis and showed that we could detect this outcome better using leveraging unstructured text in addition to codes. So in summary, there are certainly opportunities for applying text mining throughout FDA's surveillance processes, and we're working towards implementing these capabilities. the development of promising tools leads to some interesting operational challenges, like which tools provide the most gains relative to their costs, and how do we integrate them into existing infrastructure and review our workflows? How do we monitor tool performance and maintain them to ensure they continue to be fit for purpose? And this becomes a whole new layer of questions for us to address. But I think welcome challenges if we have tools that we think can meaningfully advance drug safety. So it must be close to 7 minutes, so thank you.
Thank you very much, Dr. Munoz. So this is great fodder for our discussion. The next speaker will be Professor Özlem Uzuner. Dr. Uzuner is an associate professor at the Information Science and Technology Department at George Mason University. She's also a research affiliate at CSAIL, the MIT Computer Science and Artificial Intelligence Lab. And many of you may know her from her wonderful work in organizing a number of challenges in the clinical area, starting with a number of the I2B2 challenges, and now the N2C2 challenges, which I think we are going to hear something about. So thank you, Özlem.
Thank you, Lynette. Thank you for the introduction, for the opportunity to come and talk to you all. Can everybody see my slides and hear me okay?
Yes.
Okay, thanks. So we've seen some fascinating talks today. So I thank everyone for basically setting the stage for what I want to say. So I want to tell you about the organization side of how we run evaluations for adverse drug events and the challenges that we're into. So the speakers mentioned this in the previous talks too. So they talked about data imbalance and other issues that of course affect system development. So I think the moral of this story is going to be that they're a problem for even generating the data for meaningful NLP evaluation. My conclusions are based mostly from the 2018 N2CT shared task on adverse drug events. And for background, just to get people on the same page, in this task, we annotated discharge summaries from MIMIC for a set of entities related to drugs, and that which included their ADEs and reason for administration, and we linked each of those attributes to the drug. So that's a complex annotation task, but it can be very informative if we can gather all this information together. Now, for us, starting a meaningful evaluation, of course, requires good data. So that's the first step. So I'll show you that there are challenges in getting the right data and getting the right complexity of the task. And there are challenges, of course, that carry forward to the system development, because whatever data is, that's what the solutions will reflect too. So on the data side, the first thing is to identify the right documents to annotate. And ADs are rare events. That's a great thing for humankind, but it's challenging for NLP studies because we need good samples of data in order to build reliable systems that will generalize. So you can't just randomly sample from a data set that represents the whole reality of the world and hope that you'll end up with good samples in your data for annotation, unless you have enormous annotation resources. If you do that, of course, you have some advantages there, but it's a time and labor intensive annotation. So you really need to get the right data set to annotate. Random sampling, we tried only 25% of the nodes that we drew with an ICD-10 code specifically from MIMIC had an actual AD mention in them. So imagine if we just went through and we did this like dense annotation task that I mentioned before and only had very few samples of ADs, that would not be very helpful for our task. So we focused after a manual review on discharge summaries that had at least one mention of an AD in them. So again, we're trying to get a representative sample in terms of complexity of the task and also make sure that the ADs are represented in there. So balancing the two is very challenging. Going forward, the complexity is also going to become a challenge when getting everything correctly annotated and getting to a good inter-annotator agreement. Again, there are so many elements to this task, and I won't list them all again, but they're both entities and relations that we need to identify. So doing purely manual annotations from ground up ends up giving us not enough samples to work with, right? So that will be good annotations, but then what about the samples? And of course, the time that it takes to generate the data set. So to help this along, we figured we would start with some pre-annotations with a system that we used before and that we trusted. So we used ctakes for this. And then on top of that, we did our double annotation and arbitration quality check to come up with a reasonable data set. All that, and of course, so I want you to think of this as like all these decisions come with a balancing act. For each decision, we paid a price at some point, right? And then we did take those steps knowingly to some extent, and the conclusions in the end, the observations sort of justified what we did, but we know that we are making a suboptimal decision here, right? So we are potentially introducing a bias to the annotations of that pre-annotation system instead of starting from ground up just for the sake of getting some volume. The complexity of the task also represents in the interannotator agreement. So I hope everyone can see that. This is on the left is the initial interannotator agreement numbers after initial training. So you can see the numbers on the right column are not bad. So 0.9s, high 8s, until you come to ADEs, 0.41. So the star of the show is lagging behind. The other one that is lagging behind is reason. And this is going to come back again. And we understood why this happened. It makes total sense. So on the other side, after we went through about 200 files with a lot of multiple rounds of training and consensus building, we got to 0.6 in AD annotations, and reasons got to 0.73. Everything else is in 90s and 80s, so they are much clearer to the human annotators. So this is, of course, going to reflect in the system development as well. So what we found is that the sources of annotation errors or disagreements tied back to the pre-annotations that we provided. So, well, that's, I guess, no surprise. So we traded off one sort of problem for another one a little bit, right? So we had superfluous annotations for both ADs and reasons that the annotator did not unannotate from the pre-annotations. And the other thing that started to appear here is that AD and reason, the two troublesome categories, are very easy to confuse for each other. So they're really dragging each other down. The reason for that is they're both medical events, medical problems, and their difference, semantic difference, comes from how they relate to a drug. One is the reason for administering the drug, and the other one is the outcome of having used the drug. So, and understanding that is difficult in this data, in distress summaries and mimic, even for humans. So we made some trade-offs up to here, right? So I said, okay, I want to get volumes. I'm going to pre-annotate, and I know I'm making some trade-offs to get some sample. After all that, and after including only notes that had at least one AD in them, we still had very small samples of ADs in our notes. Again, good for humankind, not good for NLP. So we have many more samples of 26,000 drugs, for example, and ADs are at 1,579. Relations linkages, of course, follow a similar pattern. So getting the right data set is tough. So that was the moral of that story. And this is going to affect, of course, the systems that we're developing as well. This is the evaluations on the same data set. So extracting concepts, all of the concepts. We just look at the average, or if you prefer, the median. The systems are doing really well on extracting concepts, actually 0.8, 0.9 concept extraction is great performance. If we have gold standard concepts and we just look at the linkages, we're at 0.8, close to 0.9, again, we are doing okay overall on the tasks. End-to-end means discover the concepts and link them. So 0.74, a slight decline, understandable. These are reasonable numbers in terms of how the systems compare to state-of-the-art in other concept extraction tasks. What is disappointing is this. So ADs here are the bottom line, the bow ties. So, and here is the top line is where the micro averages, there are many more samples there. If you look only at the ADs, we are somewhere around 0.4 on average of the top 10 systems here. The other one right above it is the reason. So that's about 0.61, 62. Everybody else is above 0.8. So AD is the thing that we're really interested in, is hard to get. If we have the gold standard entities, relations are pretty reasonable. Again, the biggest confusion is probably between reasons and ADs and the way they relate to the drug, but everybody else is pretty high up, close to 90s. And if we do an end-to-end evaluation, no surprise here, because finding the ADs is tough, finding their relations also is tough. On top of that, without using any gold standard data, we are at 0.3 kind of performance, and reasons are lagging behind the other categories as well. So there is quite a bit of work to do to learn ADs better. And what's the reason that we cannot get them? Really, it's a matter of context. The context in which that they appear is challenging. And I already mentioned reasons that ADs differentiating the two of them is challenging. But in many of the contexts that we analyzed, and none of the top 10 systems got these right, there was inference required. So imagine you already have low sample sizes that is working against you. Now you are really at the cutting edge of NLP, adding inference to extraction. So you can't do something at just lexical or syntactic level, but there is inference that needs to be done. And a lot of domain knowledge was found to be useful. So some linkage of the state-of-the-art technologies to domain knowledge that we could interpret, for example, difference between a reason and an AD of a drug would be very helpful. So overall, really, they are challenging and interesting to evaluate. So that just means we just need more of these studies in my mind. Getting the right data is challenging. Getting the right sample sizes and the right selection of data is challenging. And when you have those, finding the right context and building the systems that will link inference, domain knowledge, and state-of-the-art technologies together for their solution is interesting, and still there's room quite a bit for growth. Thank you.
Thank you so much. That is a lot of food for thought. I will just add parenthetically that this is specific to trying to get ADEs out of clinical data. Thank you. And our next panelist is Dr. Raul Rodriguez Esteban. He is a senior principal scientist at Roche Pharmaceuticals in Basel, Switzerland, where he works on natural language processing, machine learning, and real-world data analysis applied to pharmaceutical R&D. So Raul, thank you very much, and take it away.
Thanks, Lynette, and I hope you can see my slides now.
Yes, can.
So hi, everyone. I work for the pharmaceutical company Roche, as Lynette said. I'm going to talk about the topic of pharmacovigilance, but from the point of view of a pharmaceutical company. So pharmacovigilance is about monitoring adverse drug reactions, but it's more than that. It's also about monitoring erroneous handlings or misuse of medicines. For example, errors in dosing, labeling, or packaging. And additionally, it's about any changes that can happen to the known efficacy of a drug. So while pharmacovigilance is coordinated by regulatory agencies, it's pharmaceutical companies that channels most of the work. Each pharmaceutical company is responsible for the pharmacovigilance of each one of its drugs. That includes, for example, answering calls and email messages from patients or doctors. Here, I will focus specifically on the topic of monitoring scientific literature reports, which is just one part of the whole pharmacovigilance process. In this slides, you can see an example from the FAIRS database, where you can see one of these literature reports. These are related to scientific articles that mention information that is potentially relevant for the pharmacovigilance of a drug. You can see in this entry in the FAIRS database that there's an adverse event reporting that is based on an article, which it's reporting about an adverse event associated with aspirin. Others reports in this database are not necessarily related to the literature. It's one subset of them. So how do these reports come about? So within the pharmaceutical companies, we have a set of groups, people who work towards filling up these scientific reports. We run weekly and monthly literature searches for each of the drugs that we commercialize. And these searches are actually Boolean searches. They are very classical. It's nothing is, you can imagine them as being a very large, complicated Boolean searches in the end. We also have what we call these ad hoc searches, which are based on questions from, for example, regulatory agencies or doctors. We run this specifically for particular questions that we receive. From all these processes that I mentioned, we have a process of validation, documentation, and then we have a readiness, a level of readiness that allows us to address any external inspections, which can be done at any point from a regulatory agency or from a licensing partner that is selling a drug with us. We also maintain workflows internally where we keep all this information. And then these workflows have to reflect past information that we have gathered over time. Additionally, you have to imagine that we are an international company, and every national affiliate has more limited processes also for pharmacovigilance that may be focused on the things like the literature in a particular language in a certain country. So how do what are the details of these searches? Like I said, we do these classical searches that you can imagine as very complicated Boolean searches. We use abstract databases as our sources and not full text articles. But why not full text articles, right? So the full text literature is not so standardized in terms of a source. We don't have a very standard database such as Embase that is only for full text articles, although that would be very beneficial. We have to validate the searches, as I said, and this is based on past knowledge of the information that we have about the drug. There's no gold standard. There is no set of data that covers everything up to a certain point. It's based on our past experience. Transparency is very important in this process because whenever there is a review or an inspection, we need to justify all the steps that we follow, and the results that we produce have to be explained. And it's very important that this goes well, because for the teams involved, it's very important that inspections, at the end of the day, don't produce any major findings. So what are the opportunities for technology in this process that I mentioned that is so regulated? So there's still some for them. I mean, like I said, this is a major factor, the fact that we have to respond to regulatory agencies. But it doesn't mean that we cannot work with full text. If we were able to produce workflows that were consistent and validated, we could also make the life easier for the safety scientists who work with this data. For example, by reducing the level of false positives, improving the triage so that they can address the results that are most interesting first, and also highlighting the results, the parts of the results, the snippets or the passages that are most interesting. We only do some of these things partially, so this is still for us a work in progress. So you probably have already some ideas that how you could improve this process, and I think there is a space for competitions in order to improve how this is done. So I just was summarizing a bit of what we do, and don't take this as a disclaimer. This is not everything we do. It's actually a pretty complex process in general. So thanks, Lynette.
Thank you, Raul. Thank you very much. Yeah, another lots of great ideas in there. So I'm going to introduce our final panelist, Professor Graciela Gonzalez Hernandez. Dr. Gonzalez is a recognized expert in NLP applied to biomedical informatics and public health informatics. She was at the Department of Biomedical Informatics at Arizona State University before joining the University of Pennsylvania, where she's established the Health Language Processing Center within the Institute of Biomedical Informatics. And she is, of course, well known in the biocreative context for running a number of very important evaluations on social media and a leader in utilizing social media for pharmacovigilance. So Graciela, take it away.
Thank you so much, Lynette, and it's a pleasure to be here. As some of you know, biocreative was the beginning of my pathway to natural language processing, and where I decided that I could do it, despite coming in what I consider was late into this field. So it was a great experience for me, and I hope that for some of the users it has been as well, this iteration of it. So I'm going to talk today during this panel on pharmacovigilance, on the role that social media can play. So I've been funded by the National Library of Medicine for about 8 years now, 9 years, I'm in the second cycle, on a grant that was specifically designed to explore social media and its value for pharmacovigilance. So there's a few lessons that I've learned. I view the overall approach as something that can complement digital epidemiology. So this is basically epidemiological studies that use data generated outside the public health system. So data that was not generated with the primary purpose of doing epidemiology. And from that perspective, that's how I seek to mine social media. So it has the same goals as typical epidemiology. It just requires access to large data sets and advanced analytics on very noisy data, so real world data. The FDA has been pushing scientists to explore real world data as a way to complement traditional approaches. It requires challenges, and it has challenges at the methodological level, but also some ethical considerations. So I always get questions on this, how are we going to mine social media? And isn't it an invasion of privacy and so on? So I wrote a little piece on that. So if you want to check it out, it's at the NLM directors musings from the mezzanine. It's on the ethics of using social media data. So I won't even touch on that. Just rest assured that everything is cleared. Everything we do has been cleared by the Institutional Review Board at my university and others. So social media is only one form of real world data. You heard from some others, electronic health records and some other sources of real world data. Most of my work right now is on Twitter, just because the rules are pretty clear. But if we think of this real world data and social media data, a lot of people get this reaction at first, like nobody will see that in social media. So that's the number one myth. They will say it. I have examples of pretty much everything you can think of coming from social media. Starting with very detailed diagnosis, for example. So if you look at that second example there, is I've been diagnosed with obsessive compulsive disorder and anxiety, been on therapy since 2 months. So it's like the declarations can get very detailed from different people. And here, this is just a screenshot from Twitter from a search of I've been diagnosed with, in quotes. I invite you to play with that. It's pretty entertaining, and you can very easily find yourself 2 hours later wondering where your 2 hours went. So we see the fake declarations as well, like this other one that says I've been diagnosed with a chronic fear of giants. But you do get the real deal. So people out there are saying things, and we need to be listening. But we need to be listening carefully, and we need to know where to place these things, because it can get very, very deceiving at times when you just look at this massive amount of things, and you can get what seems to be distinct groups when in reality it is the same group or the same person. So there's many, many, many roadblocks on the way to actually these gems of information that we're after. So in general, it's not the same to think that data is there and that you can find it. So it is there. It doesn't always mean that you can find it. And that if you can find it, it doesn't mean you can automatically find it. And even if you can automatically find it, it doesn't mean it's valid. So validation of social media data is another one of these challenges, and it requires human annotation. It requires careful planning. It requires careful study design. And in order to make annotation scalable at the sizes of the data sets that come from social media, it definitely requires classification and other natural language processing, which leads me to the second one. So the second myth is that you can easily collect tons of data from social media. As we saw from the challenges at BioCreative yesterday, the extracting drug mentions, we saw how imbalanced the sets can be. So in a user timeline, on average, we find 0.25% of mentions that are about drugs. So we're looking at from the user perspective, we don't find a lot. But if you look at it from the drug mention perspective, then you can find a lot of mentions. So just to give you a rough idea, even though in a timeline we only see about 0.25% of the tweets being mention of a medication, on average, when we get a collection going on drug names and variants of drug names, we get a lot of hits. We get about 20 to 40,000 tweets on average per day. So it's a lot. And out of those, about 3 to 8% are mentions of adverse drug events. So we do get enough. It's just not easy to get, and you cannot just easily collect tons and tons of data. And it's not equally distributed amongst all drugs. So that's another thing. So myth number 3 defies common logic of taking it one step at a time. I will advise against taking it one step at a time in this particular field. You cannot just take it one step at a time, because you make a lot of mistakes that then basically means that you have to retrace your steps. So you have to address all the issues in a pipeline rather than one step at a time. So in NLP, we've spent the last few years looking at papers published on classifying tweets for adverse events. So just that single task, or on extracting mentions, name entity recognitions, which is the second step, and even on entity normalization, which are the fewest papers. However, each of these tasks, if disconnected from the prior task, gives you basically a false sense of security. So it will give you inflated performance, and you will kind of think that you have it solved, only to realize that everything collapses as soon as you add the step that is immediately prior to it. And we have experienced that as well in our own approaches. It's like we had a really good drug mention identifier that was performing at the 80s, 82%, only to see it collapse to almost nothing in terms of performance when we threw it into a timeline, and hence our approach now to look at timelines for the extremely unbalanced data. So I'm gonna run through this just to make sure I don't go over time. But this shows you, for example, if you look carefully, this DPDA minor is our published state-of-the-art paper. It's on JAMIA. And we saw that if we look at classification, we're around 65% F measured 0.63 in that task. Entity recognition was 78%. But when we put it all together, we're just hitting the 50s or 0.34%, depending on how you look at the task. So the performances for the pipeline from beginning to end, classification, entity recognition, and normalization of adverse drug events is still it still requires a lot of effort, which takes me to how are we going to do this? How are we going to advance? Well, we've been running a shared task for now 6 years on this particular, just in this particular problem. But we run all other things as well. But just getting from end to end, from tweets to adverse drug events, it has been running continuously for the 6 years of the social media mining for health workshop and shared tasks. We had in the last one, 2019 submitted system descriptions. So we had really good participation. They did outperform our state of the art in some of this. In classification, for example, the winner is at 0.61, or no, actually it's a little lower. Anyway, so each of the tasks was run. So we did run tweet classification, we did run span detection, but we also ran ADE resolution end-to-end. If you look at it, we're at the 0.29 on that as well for this particular task. So it is still a challenge to get the end-to-end. And the reason I mentioned that is that really social media mining for pharmacovigilance is in need of those systems. So we are much better than we were 5 years ago, definitely. So the possibility is there for advancing to what was the original intent, which was signal detection. So definitely social media provides valuable data and a unique perspective from the users, and it's worth listening. Extracting and normalizing specifically about adverse drug events, relevant adverse drug event mentions is very, very challenging. A pipeline approach to the task is essential, otherwise we're getting the wrong numbers and the wrong sense of performance. Signal detection remains an unsolved challenge. The reason for that is for signal, you need data for pretty much all the drugs out there to try to see if this particular mention of an adverse event for this particular drug exceeds the threshold of the background noise or the expected effects for all the drugs. So until you have that, you cannot really get true signal from social media. That said, the collection we have enables us to do that, but there's still challenges because we need to compare, for example, to the established corpora and so on. So it takes a lot of effort, which unfortunately right now is not funded. So that effort remained in the back burner, really to exploit what I consider the most immediate use of social media. It might be the best use of social media, mind you, but I'm not there. I cannot say that that's the best use until I explore the signal question a little more. The work that has been published on this indicated that it was not usable, and I disagree with that. It is usable. It's just that they run very old technology for NLP to do this normalization. And so it was an European effort that was funded by a few years ago. I am interested in exploring it again. It's still an open question. So it is still an unsolved challenge. The best and most immediate use, and I 100% can back this up, is for looking at protected populations, such as during pregnancy, that do not participate in clinical trials, looking at aspects of tolerability, looking at aspects of adherence, because you do get this loud and clear from the public in social media, understanding beliefs and behavior,
Nunca.
and definitely not for early detection. We got a little bit of noise coming from somewhere, not me. I promise it's not me. All right. Okay. So even though it was Spanish there. So anyway, detection is not at this point the best of or most immediate use. And actually, I will doubt that we will get there for early detection in social media. It is not what is geared to be, at least in my opinion over these years. Maybe I'm willing to be proven wrong, but that's basically the presentation that I have for today.
Mas eu já conheci esta pessoa. Mas comi ramen ao lado dela em Tóquio.
Thank you, Graciela.
You're welcome. I think somebody can mute everybody and then we can unmute.
É americana.
Just in case.
Sim, mas ainda não despi. Mas podes tirar as coisas. Metem no canto. Abre os bolsos todos.
Please do mute yourself if you're not, a speaker. We can hear some noise in the background. I think it's Portuguese, actually, not Spanish.
Ah, okay, true. Now that we hear a little more of it. Always interesting to listen to those conversations, but I don't think that's the intent. All right. So that's it. Thank you.
Oh, all right, we're back. Thank you. Oh. So, can people hear?
Yes.
Good. Yes, sorry, I have no idea what happened, but I'm glad to see that we are back. And I have unfortunately lost the chat, which has the questions, but Martin has put them back up on the slide. So I was going to start off by asking a question that Graciela may have at least partly answered in the closing of her talk. So what are the critical applications for text mining of adverse drug reactions? Who needs this? And we've heard from a number of different sources, but I'd like to start by maybe going back to Monica for the FDA perspective and just summarize briefly. And I think at this point we could probably turn on the microphone of all the panelists and see if we can get some open discussion going. You can also post your questions, I think, in either chat or Q&A, but I actually would have trouble monitoring both of them. So Monica, you want to start by sort of summarizing some of the critical applications that you would like to see?
Sure. I think we highlighted some PV applications along managing safety data, and just say it's all quite challenging with the growing volume of adverse event data that we have in each traditional source that we surveil. And when we think about evaluating new sources that may provide important insights on adverse reactions. And realistically, we have to think about this in the context of finite resources. And spontaneous reports, is obviously a big focus for us, and they actually contribute to more than half of safety-related labeling changes after a product is approved. So gains in processes around screening and evaluating these reports that may stem from text mining applications can have important public health impacts. We receive over 2 million reports a year, and this means expending more resources on initial processing of reports by FDA and industry. As Raul mentioned, 95% of reports actually come from industry, but we all need to process them in order to do anything meaningful with that information into some structured fields for different signal identification techniques and retrieving reports and so on. Aside from just the rudimentary coding of reports, the narrative of these case reports is really the heart. And in truth, not every report in the database is a gem. So if the narratives have not been read, at best you really have a hypothesis about a safety concern. And so we don't take actions without taking a look at or trying to understand the underlying narrative. They're often used to confirm a report is unique. It's not unusual to see reports describing the same drug adverse event patient because it was reported by multiple reporters. I think Raul even picked up a good example of a literature case that looked like it was duplicative in FAIRS. We read reports to find out if what was actually reported is really relevant. We often see alerts representing disproportional reporting for indications of the products or the patient's past medical history. And the narrative, of course, is essential for assessing the causal relationship between exposures and events. So, the unstructured text there is really critical to using that data source, and reviewers have an increasing amount of these narratives to consider. So I can talk about EHR data and other data sources, but I think I'll leave that to others to opine on.
Okay, and just one quick follow-up question. So if you're talking about spontaneous reports, these may contain sort of personal identifying information, correct? And as such, they are not freely available to researchers, for example. Is that correct?
Yeah, the FAIRS public dashboard has a has the database, available to researchers, but it doesn't contain protected information that may include PHI. And unfortunately, the narrative gets entirely removed from that data set.
Great. Okay. But yeah, it's not great, but anyway, thank you for the information. Yeah, Raul, anything you would like to highlight in terms of?
I actually wanted to bring another perspective that I didn't really mention, which is patient centricity. So for us, there's this big push from the FDA towards patient centricity, and this means that it's not the way that people react to drugs or their needs in terms of the disease have to be seen from their point of view. Traditionally, we have to look at those from the medical point of view, how the doctors see that. So for example, in terms of adverse drug reactions, we could see what the patients think about them, right? So how they rate them, because an adverse drug reaction may be tolerable or not tolerable, could have a different impact on a patient's life, depending on their stage of life, depending on the disease. So it's not just about the adverse drug reaction, but also the context, right? What is the context of that person? And I think social media is very powerful for that. But you can also maybe get something from that from the literature. So I think trying to learn about the context, how bad the adverse reaction is for the patient, how long does it last, whether that will make the patient not take the drug, discontinue the medication or not. Those are very important factors that we should acknowledge generally. I don't know if it's so easy for a text mining task, but it's really something that is very interesting for us.
So if I might add to that, yes, Raul, we are approaching it as one of the richness of social media, the tolerability question. We've seen it, and we are heading in that direction. The other thing that we've been doing work on, and there's also a paper published on that, is we did medication change. So there have been some prior attempts at doing adherence, but that's a more complex question. So we decided to break it into the prior questions, like when people express that they have changed their medications, regardless of whether it was per the doctor's orders or not, so that we can analyze the reasons for that change. So as I said, like as a pipeline. Oh, sorry.
Sorry, I just missed the last end of your.
We still need to address it as a pipeline rather than an individual task force. But yes, definitely, tolerability is one of the things that we see comes there, because it tells us from the patient's perspective that something that might be for purposes of fairs and reporting and official reporting, not worth it. But yet, if it's strong enough, if it's disruptive enough, then it is definitely something that can drive non-adherence and could then impact health down the road. If it's something as simple as dry mouth or dizziness that are considered minor effects, they could be, from the perspective of the patient, be very disruptive to their lifestyle, and they stop taking their meds.
Yeah, I'm going to see if Özlem wants to weigh in here, because actually some of these issues remind me of one of the earlier I2B2 tasks, in addition to the ones you're doing now. So Özlem, any comments?
Well, I mean, I think these are all great angles to the task. And in my mind, and I think it's the Holy Grail, it's not where we are, but identifying the potential of ADs and being able to do something about it before they happen is an honorable goal to keep in mind. We're not there yet, but in a clinical setting, so from all these data sets, knowing that something is a theoretical possible outcome and that has been observed in a clinical trial population in the medication, that it has been observed in social media and people have really experienced it, and add to it clinical notes where doctors have observed it, putting them together would empower us to do something about adverse drug events before they happen. And there's a huge challenge in doing that, of course, that these data sets are not, they speak completely different languages, and they are not even coordinated, and we all took our best stab at formulating the task, and the tasks are not even the same across the data sets. But I think there is a lot of power in actually doing something about adverse drug events themselves, preventing them by learning from all the sources that we have. That's something I'd like to see, but it requires a lot of work. We're not yet there.
Great. And Martin, you want to weigh in here?
Yes, so I think one issue here is really, if we put it in the context of BioCreative, what are the kind of data content which can actually be shared and which can be accessed and prepared in a way that you are able to label or provide some sort of gold standard or annotated data collection. So we already saw the issues with privacy, the problem with selecting and finding the appropriate data, and the potential bias in there. So my point of view is here is that what are the kind of resources which currently do critically need text mining systems because they are not being captured. I'm thinking about gender related issues, or like ethnicity of some of these patient groups where maybe text mining could contribute, and they're not routinely, examined appropriately, or even more at the preclinical level. So we are looking here in this panel a lot on like the clinical setting, but you have to take into account that some of these aspects can actually be captured or traced back to in vivo preclinical studies, and some of them are also published in the literature even after the drugs are approved. So there are multiple sources, each with a different kind of value. What I think would be important is to keep in mind what we can actually share and annotate and prepare in a way that you can generate this kind of application for text mining systems. So that's my concern here.
Thank you. I want to take a really interesting question that Bernal Jimenez Gutierrez posed. It seems like ADEs are not entities, but rather relations between drugs and symptoms. Why do we define ADE extraction as an entity extraction task instead of structuring it as a relation extraction task on top of symptom and drug extraction? So that's a very good question.
Yeah, it is a good possibility. However, the way that this taking it entity by entity, there's a couple things that happen. Most of the time you get a single drug mentioned. Sometimes you do have two drugs mentioned in one tweet. And there's more than one thing in there. So we have approached it as an entity rather than a relationship. One, because the models are simpler, and two, that classifiers can handle the distinctions that we care most about, which is this an ADE or is it an indication? Those are the main two things that appear in conjunction with a drug. So many times adding the complexity of relation for all the tweets of relationship extraction to all the tweets will be an overkill. So you could, for example, break it into two steps, and those tweets that have two drugs or that have what could be ambiguous mentions of either indications or adverse effects that cannot be sorted out, they could go into a next step in the pipeline. So rather than changing the whole model for the few, I personally prefer the aspect where you deal with everything that is low-hanging fruit and can be handled as just an entity, and then you can have another step in the pipeline to deal with other ambiguous things. So it is not that we just ignore the fact, it's just that most of the times the tweets are so short that it's really okay to just treat them like that, because you identify the drug step as a separate step, and then you just analyze any symptom mentioned in context with classifiers that tell you if it's an adverse effect or it is an indication. And we have annotations like that, or annotations have indication.
Okay, well, we're just Gracielo's audio, but I want to give a slightly different answer and maybe call on Monica to back me up here. But one of the reasons I treat it like entities is there is a vocabulary for talking about adverse drug events, namely MEDRA. So Monica, you have any comments on that?
when you think about the target of MedDRA or dictionaries, we speak in MedDRA in our case report data and clinical trial data, even in our internal tracking system where we track safety issues, even preclinical, they all connect to each other, and MedDRA is the primary dictionary. And just a comment on the general terminology of ADE versus ADR. A drug event, could be something that occurs in the context of the use of the product, but may not necessarily reach that level of a reaction, which is a causal relationship, which we're most interested in.
Great. So you're distinguishing between ADEs and ADRs, and yes, that's certainly an important distinction. But also gets to what the target output is. I mean, Martin just emphasized the need to, at least for text mining applications now, in terms of constructing challenge evaluations, data needs to be available, accessible, and shareable. But the other thing that we always look for in BioCreative is having some appropriate target output. And so MedDRA is one class of output that is relevant for certainly FDA kinds of applications. For the clinical data, there are other possibilities. And how has clinical data been encoded? And Aslan, that maybe
we've done it both ways. Yeah, we've done it both ways, Lynette. I mean, that's a great question. So normalization does throw some need for consistency with the rest of the field, but in clinical notes, we've done it both ways, where you mark the entity with its semantic type. So if it's a medical problem, but it's an ADE, you mark it as an AD as opposed to a medical problem, and then leave the AD part to the relationship to the drug. We've done it both ways. It's you're trade off one sort of complexity for another one in that case. And as long as you are building a structured representation, which you can then map to the normalization output, I think either of them would work fine. In one of them, you would have the relation represented in a different way in the structured form based on the more general entity, as opposed to having the entity carry that relation with it. For a data that is actually plagued with sparsity everywhere, it is an empirical test, which representation would be more conducive to NLP outcome system development. I can see benefits of both, and we've done it both ways.
I see we're basically at time, but I'm gonna, I know Martin has dealt with a lot of preclinical data. So Martin, do you have ideas about what target output should be used?
So I think what would be beneficial is to have like different complementary scenarios. So I guess there's not like a single solution. It depends really on how you're exploiting the data. What we saw from like the preclinical data, but also in terms of some of the clinical data, is that annotating the, like, let's say the adverse drug event or even like symptoms is far from solved, and you might have like long range association. If you read the record, you know that there's some alteration of liver enzymes that don't explicitly state hepatotoxicity, but you immediately know there's adverse reaction based on some drug administration, and they withdraw it. So I think it might be oversimplistic to actually see it as a relation extraction task. And there are obviously things which are in the literature and which are common in terms of human data and preclinical data. So in this sense, what I think could be feasible is actually to build on the detection of drugs, which we know work very well, and then think about maybe one task where you classify or rank the drugs depending on the context, where there's some other adverse drug reaction described for this drug, or maybe have a second track where you have this more classical relation extraction. So both things I think very valid.
Great. And Raul, let me just come back to you for any last thoughts on this.
About the task, right? I think they are very worthy topics discussed here. I think the toxicology field, as you know, is really going through advancing towards a more digitalization, so trying to use less animals, right? And also the idea of translation, right? So like Martin said, trying to understand what the models, what your toxicology data means for the patients in the end. So that's a really interesting task out for us. Maybe just in order for you to think, the way we think about the patient is within a disease, right? And we think of their unmet need, right? So there's an unmet need based on the drugs that they are taking, and because those are the ones that are available, but they may be open for other medicines because of these drugs are not, they have adverse reactions or other characteristics, and then a lot of contextual information about their lives. So we try to see patients in that sense, right? And this information about that we can gather from toxicology, that we can gather from existing adverse drug reactions for existing drugs, allow us to think about the new medicines that we want to develop, right? So there are many angles that we can, where adverse drug reactions can be useful, and in the sense, I mean, maybe just text mining has to build around different areas in order to get the full picture, right? So that's how the way we think about it.
Okay, thank you so much to all the panelists. I think where I'm going to call this here because we are out of time, but we can certainly keep the question answering open, and we really appreciate it. We will most likely write this up, and love to hear your reactions. Thank you very much to the panelists.
Thank you.
Thank you.
Thank you.